What if the vast distances separating galaxies weren't the insurmountable barrier we've always believed them to be? What if there was a way to bypass the constraints of space and time, allowing us to travel from one corner of the universe to another in the blink of an eye? This isn't the stuff of science fiction, it's the tantalizing promise of wormholes, theoretical tunnels through the fabric of spacetime that could forever change how we explore the cosmos. Today, we're diving into 45 groundbreaking wormhole theories, each offering a unique glimpse into how these cosmic shortcuts might work and what they could mean for the future of interstellar travel. From the mind-bending physics that make them possible to the revolutionary technologies they might inspire, we'll uncover how wormholes could hold the key to humanity's dreams of reaching the stars. So, are you ready to explore the mysteries of the universe and discover how these cosmic portals might one day become our gateway to the beyond? Let's begin. To truly understand wormholes, we need to travel back in time, not through a cosmic shortcut, but to the early 20th century when the foundations of modern physics were being laid. It was here, in the midst of Albert Einstein's groundbreaking work on general relativity, that the first seeds of wormhole theory were planted. In 1935, Einstein and his colleague Nathan Rosen proposed something extraordinary, a theoretical bridge connecting two distant points in spacetime. Known today as the Einstein-Rosen bridge, this idea was born from their attempts to solve equations describing the behavior of gravity and spacetime. At its core, the concept suggested that spacetime could curve and fold in such a way that a tunnel, a shortcut, might form between two regions of the universe. At the time, this idea was met with both fascination and skepticism. Many physicists saw it as a mathematical curiosity rather than a physical possibility. After all, the equations of general relativity allowed for such structures, but they also hinted that these bridges would be incredibly unstable, collapsing almost instantly under their own gravitational forces. Yet, the mere existence of this possibility opened the door to a new way of thinking about the universe. As physicist John Wheeler later remarked, the universe is not only stranger than we imagine, but stranger than we can imagine. Over the decades, the Einstein-Rosen bridge evolved from a theoretical oddity into a cornerstone of modern wormhole research. Scientists began to explore whether these structures could be stabilized, perhaps with exotic forms of matter or energy that counteract their tendency to collapse. This shift marked the beginning of a new era in physics, one where wormholes were no longer seen as mere mathematical artifacts, but as potential gateways to the stars. From these humble beginnings, the study of wormholes has grown into a vibrant field, with 45 distinct theories now offering unique perspectives on how these cosmic shortcuts might function. Each theory builds on the work of Einstein and Rosen, pushing the boundaries of what we thought was possible and opening up new horizons for interstellar travel. As we delve deeper into these theories, it's worth reflecting on how far we've come since those early days. What started as a speculative idea has blossomed into a rich tapestry of scientific inquiry, one that continues to challenge our understanding of the universe. And while the journey from theory to reality is still far from complete, the progress we've made is a testament to the power of curiosity and imagination. So, let's take a closer look at how these ideas have evolved and what they might mean for the future of space exploration. Imagine a long, winding road stretching across a vast desert. The journey from one end to the other could take hours or even days, but what if you could fold that desert in half, bringing the two ends together and creating a shortcut? This is the essence of a wormhole, a theoretical tunnel through spacetime that connects two distant locations, allowing for travel that would otherwise be impossible under the constraints of light speed. At its core, a wormhole is a solution to Einstein's equations of general relativity, suggesting that spacetime isn't just a flat, unchanging stage, but a dynamic, malleable fabric that can bend, fold, and even tear. To better understand this, let's use a simple metaphor. Picture a piece of paper with two dots drawn on opposite ends. The distance between them represents the immense stretch of space between 2 points in the universe. Now, fold the paper so the dots overlap. If you poke a hole through the folded paper, you've created a shortcut, a wormhole, that allows you to travel between those points almost instantaneously. In reality, spacetime isn't paper, but this analogy helps illustrate how wormholes could bypass the vast distances that separate stars, galaxies, and even universes. Now, let's dive a little deeper into the science. Every wormhole has two key features, an event horizon and a throat. The event horizon is the point of no return, the boundary beyond which anything that enters is pulled inexorably toward the center of the wormhole. It's similar to the event horizon of a black hole, but with one crucial difference. Instead of leading to a singularity, the wormhole's throat connects to another region of spacetime, potentially offering an escape route. The throat is the tunnel itself, the bridge between the two ends of the wormhole. Depending on the theory, this tunnel could be traversable, allowing matter and energy to pass through, or it could collapse almost immediately, making it a one-way trip to oblivion. While the concept of wormholes might sound like science fiction, it's grounded in the same principles that govern black holes and the expansion of the universe. The equations of general relativity allow for their existence, but they also suggest that creating or maintaining a stable wormhole would require exotic forms of matter or energy, substances with negative mass or energy that defy our everyday understanding of physics. These exotic materials would be necessary to keep the wormhole's throat from collapsing under the immense gravitational forces at play. So, why does this matter? Wormholes aren't just fascinating thought experiments. They represent a potential solution to one of humanity's greatest challenges, interstellar travel. The distances between stars are so vast that even with our fastest spacecraft, reaching the nearest star system would take thousands of years. But if wormholes exist, or if we could one day create them, they could serve as cosmic shortcuts, reducing travel times from millennia to mere moments. It's an ambitious vision, but one that has captivated scientists and dreamers alike for decades. As we explore this idea further, it's important to remember that wormholes come in many shapes and sizes, each with its own unique properties and challenges. From traversable wormholes to those that exist only for an instant, the possibilities are as varied as they are intriguing. And as we'll see in the next section, these different types of wormholes open up a universe of possibilities and challenges for the future of space exploration. Not all wormholes are created equal. In fact, the distinction between traversable and non-traversable wormholes is one of the most critical factors in determining whether these cosmic shortcuts could ever become a reality for interstellar travel. A traversable wormhole, as the name suggests, is one that allows matter, and potentially humans, to pass through it safely. Think of it as a cosmic subway, shuttling travelers from one point in spacetime to another without collapsing or destroying them in the process. On the other hand, non-traversable wormholes are more like cosmic cul-de-sacs. They might exist mathematically, but they're unstable or impassable, collapsing almost instantly or trapping anything that enters them. The difference lies in the physics that govern their structure. For a wormhole to be traversable, its throat, the tunnel connecting its two ends, must remain open long enough for something to travel through it. This requires a delicate balancing act, as the immense gravitational forces at play would naturally cause the wormhole to collapse. Here's where exotic matter comes into play. Unlike ordinary matter, which has positive mass and energy, exotic matter possesses negative energy density. This bizarre substance could, in theory, counteract the gravitational forces trying to close the wormhole, keeping it stable and open for travel. The catch: exotic matter has never been observed in nature, and its existence remains purely theoretical. Science fiction has long been fascinated with the idea of traversable wormholes, often portraying them as gateways to distant galaxies or even alternate universes. Take, for example, the iconic Stargate from the Stargate franchise, a device that creates a stable, traversable wormhole, allowing instant travel between planets. Or consider Christopher Nolan's Interstellar, where a wormhole near Saturn serves as humanity's lifeline to a new home among the stars. While these depictions are dramatized, they capture the essence of what traversable wormholes could offer: a way to transcend the vast distances of space and time. But the challenges of creating such a wormhole are immense. Beyond the need for exotic matter, there's the issue of size. Theoretical models suggest that most wormholes would be microscopic, far too small for anything larger than a particle to pass through. Scaling them up to human proportions would require an unimaginable amount of energy and precision. And even if we could overcome these hurdles, there's the question of navigation. How would we control where a wormhole leads? How would we ensure it doesn't deposit travelers into the heart of a star or the void of empty space? Despite these challenges, the idea of traversable wormholes remains a tantalizing possibility. Some physicists have proposed that advanced civilizations might one day harness the power of quantum mechanics or manipulate spacetime itself to create stable wormholes. Others suggest that naturally occurring wormholes could exist, hidden in the fabric of the universe, waiting to be discovered. While these ideas are still in the realm of theory, they push the boundaries of what we believe is possible, inspiring scientists and dreamers alike to imagine a future where the stars are within reach. As we explore these possibilities, it's worth considering how theoretical breakthroughs could bring us closer to making traversable wormholes a reality. From new insights into quantum gravity to advancements in energy manipulation, the path to stable wormholes is paved with challenges, but also with extraordinary potential. And as we'll see in the next section, the journey to unlocking these cosmic shortcuts is just as fascinating as the destinations they might lead us to. The concept of exotic matter might sound like something out of a futuristic novel, but it's a cornerstone of wormhole theory and one of the most puzzling ideas in modern physics. To understand why exotic matter is so crucial, let's start with a simple question: what keeps a wormhole open? The answer lies in the delicate balance between gravity and energy. Gravity, as we know, pulls everything inward, and in the case of a wormhole, it would naturally cause the tunnel to collapse. To counteract this, physicists hypothesize that a special kind of matter, exotic matter, could provide the necessary repulsive force to keep the wormhole stable. Exotic matter isn't like the stuff we encounter in our everyday lives. It's theorized to have negative energy density, meaning it exerts a kind of anti-gravity effect. Instead of pulling things together, it pushes them apart. This bizarre property is what makes exotic matter so intriguing and so controversial. As physicist Kip Thorne once put it, exotic matter is the key to traversable wormholes, but it's also the most speculative part of the puzzle. The challenge, of course, is that exotic matter has never been observed in nature. It exists only in the equations of theoretical physics as a solution to the problem of wormhole stability. This hasn't stopped scientists from exploring its potential, though. Some have suggested that exotic matter could be created in highly controlled laboratory conditions, perhaps by manipulating quantum fields or harnessing the strange properties of the vacuum of space. Others argue that it might exist in tiny quantities in certain regions of the universe, waiting to be discovered. One of the most fascinating aspects of exotic matter is how it defies our conventional understanding of physics. According to the laws of thermodynamics, energy cannot be negative. It's a fundamental principle that underpins much of our scientific knowledge. Yet, wormhole theory suggests that exotic matter would need to violate this principle, creating a kind of energy that's less than zero. This contradiction has led some physicists to question whether exotic matter could ever exist, while others see it as an opportunity to rethink our understanding of the universe. Despite the controversy, the search for exotic matter remains a vibrant area of research. Some theories even propose alternatives to exotic matter, such as using quantum entanglement or higher dimensional physics to stabilize wormholes. These ideas are still in their infancy, but they represent exciting new directions in the quest to unlock the secrets of wormholes. As we continue to explore these possibilities, one thing is clear: the role of exotic matter in wormhole stability is more than just a scientific curiosity. It's a gateway to understanding the deeper mysteries of the universe. Whether exotic matter exists or not, the questions it raises challenge us to think beyond the limits of conventional physics and imagine what might be possible in the far reaches of spacetime. And as we'll see in the next section, the journey to uncovering these mysteries is just as fascinating as the wormholes themselves. What if the strange and seemingly magical behavior of particles at the quantum level held the key to understanding wormholes? This is the heart of the ER=EPR conjecture, a bold idea that connects quantum entanglement, one of the most perplexing phenomena in physics, with the theoretical tunnels through spacetime we call wormholes. The name itself is a shorthand for the groundbreaking work of Albert Einstein, Boris Podolsky, and Nathan Rosen, who first described quantum entanglement in a famous 1935 paper, and the Einstein-Rosen bridges that laid the foundation for wormhole theory. At its core, quantum entanglement is a phenomenon where two particles become so deeply linked that the state of one instantly influences the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance because it seems to defy the classical laws of physics. But what if this spooky connection wasn't just a quirk of quantum mechanics? What if it was evidence of something far more profound, tiny, microscopic wormholes threading through the fabric of spacetime, connecting entangled particles across vast distances? This is where the ER=EPR conjecture comes in, proposed by physicists Juan Maldacena and Leonard Susskind in 2013. The idea suggests that entangled particles are linked by tiny wormholes, effectively creating a bridge between them. In this view, entanglement isn't just a mysterious connection, it's a physical manifestation of spacetime itself. Imagine two distant points on a sheet of paper. If you fold the paper and poke a hole through it, you create a shortcut between those points. In the same way, entangled particles might be connected by these minuscule wormholes, allowing information to flow between them instantaneously. To make this more tangible, let's use an analogy. Think of entangled particles as two friends on opposite sides of the world, each holding one end of an invisible string. No matter how far apart they move, the string remains taut, connecting them. Now, imagine that this string isn't just a metaphor, it's a real, physical tunnel through space-time. This is the essence of the ER=EPR conjecture. Entanglement and wormholes might be two sides of the same cosmic coin. Of course, this idea raises as many questions as it answers. For one, if entangled particles are linked by wormholes, what does that tell us about the nature of spacetime itself? Could the fabric of the universe be woven together by an intricate web of these microscopic tunnels? And if so, could we one day harness this connection to create larger, traversable wormholes for interstellar travel? While these questions are still the subject of intense debate, the ER=EPR conjecture has already reshaped how physicists think about the relationship between quantum mechanics and general relativity. It's a tantalizing glimpse into a deeper unity that might underlie the laws of the universe, a unity where the strange behavior of particles and the bending of spacetime are intimately connected. As we ponder these ideas, it's worth reflecting on how far we've come in our understanding of the cosmos. From Einstein's equations to the quantum realm, the journey to uncover the secrets of wormholes has been as much about reimagining the universe as it has been about exploring it. And as we'll see in the next section, this journey takes us to one of the most enigmatic objects in the cosmos, black holes. These cosmic giants might not just be the endpoints of collapsed stars, they could also hold the key to unlocking the mysteries of wormholes. Black holes have long captivated our imagination, often portrayed as cosmic monsters lurking in the depths of space, devouring everything that comes too close. But what if these enigmatic objects aren't just endpoints of collapsed stars? What if they're also gateways, potential entrances to wormholes that could lead us to distant corners of the universe? This idea might sound like science fiction, but it's grounded in the same physics that describes how black holes warp spacetime. To understand this connection, let's start with what we know about black holes. When a massive star exhausts its fuel and collapses under its own gravity, it forms a region of spacetime where gravity is so intense that nothing, not even light, can escape. This point of no return is called the event horizon, and beyond it lies the singularity, a point of infinite density where the laws of physics as we know them break down. But here's where things get interesting. Some theories suggest that instead of leading to a singularity, certain types of black holes could connect to wormholes, effectively creating a bridge to another part of the universe. The key to this idea lies in the geometry of spacetime. Just as a wormhole is a tunnel connecting two distant points, a black hole could, in theory, serve as one end of that tunnel. Imagine a funnel with a narrow neck, the black hole's event horizon, and a widening tube that leads to another funnel on the other side. This second funnel could open into a completely different region of spacetime, perhaps even another universe. The challenge, of course, is surviving the journey. The intense gravitational forces near a black hole's event horizon would stretch and compress anything that enters, a process known as spaghettification. For a human traveler, this would be fatal, but what if wormholes offered a safer alternative? Unlike black holes, which are one-way tickets to destruction, a stable wormhole could provide a traversable path through spacetime. Instead of being crushed by gravity, a traveler could pass through the wormhole's throat and emerge unscathed on the other side. This raises an intriguing possibility. Could black holes and wormholes be two sides of the same cosmic coin? Some physicists think so, suggesting that certain black holes might naturally connect to wormholes, creating a network of shortcuts through the universe. Recent astrophysical discoveries have added fuel to this idea. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's event horizon, revealing the eerie glow of matter swirling into the abyss. While this image didn't show a wormhole, it provided a glimpse into the extreme conditions near a black hole's boundary, where spacetime is stretched to its limits. These observations are helping scientists refine their models of how black holes and wormholes might interact, offering clues about the potential for such connections. But the relationship between black holes and wormholes doesn't stop at space travel. It also hints at something even more extraordinary: the possibility of time travel. If a wormhole connects 2 points in spacetime, it could, in theory, link not just distant locations but also different moments in time. This idea, first proposed by physicist Kip Thorne in the 1980s, suggests that wormholes could serve as time machines, allowing travelers to move not just through space but also through time. As we explore these ideas, it's worth reflecting on how they challenge our understanding of the universe. Black holes, once thought to be purely destructive, might also hold the key to unlocking the secrets of wormholes and the mysteries of time itself. And while the journey from theory to reality is still fraught with challenges, the possibilities are as thrilling as they are profound. So, as we turn our gaze to the next frontier, wormholes as time machines, we're reminded that the cosmos is full of surprises waiting to be discovered. The idea of time travel has fascinated humanity for centuries, from the tales of H.G. Wells to the iconic DeLorean in Back to the Future. But what if time travel isn't just a fantasy? What if wormholes could make it a reality? This brings us to one of the most mind-bending aspects of wormhole theory: their potential to serve as time machines. At the heart of this idea lies a concept known as closed, time-like curves, paths through spacetime that loop back on themselves, effectively allowing an object or person to travel back in time. To understand how this works, let's start with the basics. Imagine a wormhole connecting 2 points in spacetime. If one end of the wormhole were moved at near light speed, perhaps by attaching it to a high-speed spacecraft, time would pass more slowly for that end due to the effects of special relativity. This means that while one end experiences only a few minutes, the other end might age by years or even decades. If you were to step into the slower-moving end, you'd emerge from the other side in the past, effectively traveling backward in time. This scenario isn't just a flight of fancy. It's grounded in the equations of general relativity. Physicist Kip Thorne first proposed this concept in the 1980s, showing that wormholes could, in theory, create closed time-like curves. But with this possibility comes a host of paradoxes and challenges. Perhaps the most famous of these is the grandfather paradox. Imagine traveling back in time and accidentally preventing your grandparents from meeting. If they never meet, your parents, and by extension, you, would never be born. But if you were never born, how could you have traveled back in time to alter their meeting in the first place? This paradox isn't just a thought experiment. It highlights the deep complexities of time travel. If the past can be changed, it raises questions about causality, the flow of time, and the very nature of reality. Some scientists argue that such paradoxes make time travel impossible, while others suggest that the universe might have built-in mechanisms to prevent them. For example, the Novikov self-consistency principle proposes that any actions taken by a time traveler would inherently align with events that have already occurred, ensuring that the past remains unchanged. To bring this idea to life, let's use a simple analogy. Think of time as a river flowing in one direction. A wormhole acting as a time machine would be like a whirlpool in that river, creating a loop that allows you to return to an earlier point. But just as a whirlpool doesn't change the overall flow of the river, a time-traveling wormhole might not alter the course of history. Instead, it could create a self-consistent loop where events unfold in a way that avoids paradoxes. Of course, this is just one interpretation, and the debate is far from settled. Some theories suggest that time travel could create alternate timelines, branching off into parallel universes where changes to the past don't affect the original timeline. Others propose that quantum mechanics might hold the key to resolving these paradoxes, with the strange behavior of particles offering a way to navigate the complexities of time travel. As we ponder these possibilities, it's worth reflecting on what they mean for our understanding of the universe. Wormholes as time machines challenge us to rethink not just how we move through space, but how we experience time itself. They push the boundaries of physics, forcing us to confront questions that blur the line between science and philosophy. And while the challenges are immense, from the stability of wormholes to the paradoxes of time travel, they also represent an extraordinary opportunity. By exploring these ideas, we're not just dreaming of a future where time travel is possible, we're uncovering new ways to understand the fabric of reality. So, as we turn our attention to the next frontier, how some theories propose solutions to these paradoxes, we're reminded that the journey to unlock the secrets of the universe is as thrilling as the destinations we might one day reach. What if the key to creating a wormhole lies in the strange and counterintuitive behavior of the quantum world? Enter the Casimir effect, a phenomenon so subtle yet so powerful that it might hold the secret to generating the negative energy required for wormhole stability. Named after Dutch physicist Hendrik Casimir, who first predicted it in 1948, this effect arises from the quantum vacuum, the so-called empty space that's actually teeming with fleeting particles and energy fluctuations. Here's how it works. Imagine placing two uncharged metal plates extremely close together in a vacuum. At such tiny distances, the quantum vacuum between the plates becomes restricted, causing the energy density there to drop below that of the surrounding space. This creates a kind of negative pressure, pulling the plates together. While the force is minuscule, the implications are enormous. The Casimir effect demonstrates that the vacuum of space isn't truly empty. It's a dynamic, fluctuating sea of energy that could, in theory, be harnessed to create the exotic matter needed to stabilize a wormhole. Physicists have long speculated that this negative energy could be the missing piece of the wormhole puzzle. As physicist Matt Visser once put it, the Casimir effect provides a tantalizing glimpse of how we might generate the negative energy densities required for traversable wormholes. But here's the catch. While the effect has been experimentally confirmed, the amount of negative energy it produces is incredibly small. Scaling it up to the levels needed for a human-sized wormhole would require technological advancements far beyond our current capabilities. Still, the potential is there. Some researchers have proposed that advanced civilizations might one day manipulate the quantum vacuum on a massive scale, using it to create and sustain wormholes. Others suggest that naturally occurring quantum phenomena, like the Casimir effect, could already be influencing the fabric of spacetime in ways we're only beginning to understand. Whether we're talking about lab experiments or cosmic-scale engineering, the Casimir effect offers a compelling pathway to exploring the boundaries of physics and the possibilities of interstellar travel. As we consider these ideas, it's worth reflecting on how the quantum world continues to surprise us. What seems like a small, esoteric effect could one day become the foundation for humanity's greatest leap into the cosmos. And as we turn our attention to the next frontier, string theory, and its role in wormhole research, we're reminded that the universe is full of hidden connections waiting to be uncovered. String theory often feels like the ultimate puzzle box of physics, a framework that promises to unlock the deepest secrets of the universe, but only if we're willing to think far beyond the three dimensions we're used to. At its core, string theory suggests that the fundamental building blocks of reality aren't particles, as we've long believed, but tiny, vibrating strings. These strings can oscillate in different ways, giving rise to everything from electrons to photons. But here's where it gets truly mind-bending. For the math to work, these strings need to vibrate in a space with more than just the three spatial dimensions we experience. In fact, string theory requires 11 dimensions to fully describe the universe. So, what does this have to do with wormholes? If the universe has hidden dimensions we can't perceive directly, they might provide the scaffolding for wormholes to exist. Imagine our three-dimensional world as the surface of a sheet of paper. Now, picture that paper floating in a higher dimensional space. A wormhole could be like a fold in that paper, connecting two distant points by dipping into a dimension we can't see. This idea isn't just speculative. It's a key part of how string theorists envision spacetime working on the smallest scales. To make this more concrete, let's introduce another concept from string theory: branes. Short for membranes, branes are multidimensional surfaces that can exist within higher dimensional space. Think of them as vast, multidimensional sheets floating in the cosmic ocean. According to some theories, our entire universe could be a three-dimensional brane embedded in a higher dimensional space. Now, if two branes were to intersect or overlap, they could create a bridge, a wormhole between them. This intersection wouldn't just connect two points in space. It could link entire universes or even different regions of the same universe. Visualizing this can be tricky, so let's use an analogy. Picture two sheets of paper floating parallel to each other in midair. If you poke a hole through both sheets and connect them with a tube, you've created a simple model of how branes might form a wormhole. In this analogy, the sheets are the branes, and the tube is the wormhole. Of course, in reality, these branes and wormholes exist in dimensions far beyond our everyday experience, but the principle remains the same. Higher dimensions could provide the necessary framework for wormholes to exist. This idea isn't just theoretical, it has profound implications for our understanding of the universe. If higher dimensions and branes are real, they could explain not only the existence of wormholes, but also other mysteries, like the nature of dark energy or the unification of gravity with the other fundamental forces. It's a bold vision, one that challenges us to rethink everything we thought we knew about space, time, and reality itself. As we delve deeper into these ideas, it's worth reflecting on how they connect to another groundbreaking concept: the holographic principle. This principle suggests that all the information in a volume of space can be encoded on its boundary, much like a hologram. Intriguingly, this idea has deep ties to both string theory and wormhole research, hinting at a deeper unity in the laws of physics. And as we'll explore next, this unity could hold the key to understanding how wormholes, and perhaps even the universe itself, are structured. The journey from string theory to the holographic principle is a fascinating one, filled with twists and turns that challenge our understanding of reality. But as we'll see, it's also a journey that brings us closer to unlocking the mysteries of the cosmos, and perhaps even our place within it. The holographic principle is one of the most mind-bending ideas in modern physics, and it might just hold the key to understanding the true nature of wormholes. At its core, this principle suggests that our three-dimensional universe, with all its stars, galaxies, and cosmic wonders, could actually be a projection of information encoded on a two-dimensional boundary. It's like a cosmic hologram, where the illusion of depth and volume emerges from a flat surface. But how does this connect to wormholes, and what does it mean for our understanding of space-time? To grasp this concept, let's start with a simple analogy. Imagine a movie projected onto a screen. The vivid images, the sense of depth, the illusion of movement, all of it is created by light shining through a flat, two-dimensional film. In the same way, the holographic principle proposes that the three-dimensional universe we experience might be projected from a two-dimensional surface, like the boundary of a black hole or the edge of the observable universe. This idea, first proposed by physicist Gerard T. Hooft and later expanded by Leonard Susskind, challenges our conventional view of reality, suggesting that the universe is fundamentally informational rather than physical. Now, where do wormholes fit into this picture? If the universe is a hologram, then wormholes might be more than just tunnels through space-time. They could be intricate connections between different regions of this holographic boundary. Think of it like a network of threads woven into the fabric of the cosmos, linking distant points not just in space, but in the underlying information that defines reality itself. As physicist Juan Maldacena put it, the holographic principle suggests that space-time and gravity emerge from quantum entanglement, and wormholes could be the physical manifestation of that entanglement. This idea has profound implications for how we understand the universe. If wormholes are tied to the holographic boundary, they might not just be shortcuts through space. They could also encode fundamental information about the structure of space-time. Some theories even suggest that wormholes could act as cosmic conduits, transferring information between different parts of the holographic universe. This would mean that wormholes aren't just passive tunnels. They're dynamic, information-rich structures that play a vital role in the cosmic order. To bring this concept to life, let's use another analogy. Picture the universe as a vast, intricate tapestry. Each thread represents a piece of information, and the patterns they create define the fabric of space-time. Wormholes, in this view, are like knots or loops in the tapestry, connecting different parts of the design. These connections could allow information, and potentially even matter, to flow seamlessly between distant regions, creating a unified, interconnected cosmos. But what does this mean for interstellar travel? If wormholes are indeed tied to the holographic boundary, they could offer a way to traverse vast cosmic distances by tapping into the underlying informational framework of the universe. Instead of moving through physical space, a traveler might navigate the holographic code that defines reality, effectively bypassing the limitations of distance and time. It's a revolutionary idea, one that could redefine how we explore the cosmos. As we consider these possibilities, it's worth reflecting on how far we've come in our understanding of the universe. From Einstein's equations to the holographic principle, each new discovery challenges us to rethink what we thought we knew about space, time, and reality itself. And while the journey to unlocking the secrets of wormholes is still in its early stages, the progress we've made is a testament to the power of curiosity and imagination. So, as we turn our attention to the next frontier, how wormholes could revolutionize interstellar travel, we're reminded that the cosmos is full of surprises waiting to be discovered. What seems like science fiction today could be the foundation of tomorrow's greatest breakthroughs, and who knows, the key to exploring the stars might already be encoded in the very fabric of the universe. What if the dream of exploring distant stars didn't require centuries-long journeys or generational spacecraft? What if, instead of battling the vast emptiness of space, we could simply step through a cosmic doorway and emerge light years away in an instant? This is the tantalizing promise of wormholes as the ultimate shortcut for interstellar travel. Unlike conventional propulsion methods, which are limited by the speed of light and the immense distances between stars, wormholes offer a way to bypass these constraints entirely. By folding spacetime itself, these theoretical tunnels could connect distant points in the universe, making the impossible not just possible, but potentially routine. Imagine a future where humanity isn't bound by the limits of our solar system. With wormholes as gateways, we could travel to Proxima Centauri, our nearest stellar neighbor, not in thousands of years, but in the time it takes to walk through a door. This wouldn't just revolutionize space travel, it could make interstellar colonization a reality. Entire civilizations could flourish on planets orbiting distant stars, connected by a network of wormholes that turn the cosmos into a bustling interstellar community. The implications are staggering: access to new resources, the spread of cultures across the galaxy, and the possibility of encountering extraterrestrial life. Science fiction has long explored this idea, painting vivid pictures of what such a future might look like. In Carl Sagan's Contact, a massive wormhole near Saturn serves as humanity's gateway to an advanced alien civilization. The Stargate franchise takes this concept even further, with a series of ancient devices creating stable wormholes that allow instant travel between planets. While these stories are fictional, they capture the essence of what wormholes could offer: a way to transcend the vastness of space and bring the stars within reach. But how does this compare to the reality of conventional space travel? Today, even our most advanced spacecraft would take tens of thousands of years to reach the nearest star. The challenges are immense: the need for vast amounts of fuel, the dangers of cosmic radiation, and the psychological toll of long-duration spaceflight. Wormholes, on the other hand, could make these obstacles irrelevant. Instead of spending lifetimes traveling through empty space, we could step through a wormhole and arrive at our destination almost instantly. It's a vision that transforms the cosmos from an insurmountable void into a navigable web of interconnected pathways. Of course, this vision isn't without its challenges. Creating or locating a stable wormhole would require breakthroughs in physics and engineering that are far beyond our current capabilities. And even if we could find one, there's the question of how to control where it leads. Could we ensure that stepping through a wormhole wouldn't deposit us into the heart of a star or the void of empty space? These are just some of the hurdles that stand between us and the reality of wormhole travel. Despite these challenges, the potential rewards are too great to ignore. Wormholes could unlock a future where humanity isn't confined to a single planet or star system. They could open the door to a universe teeming with possibilities, where the stars are no longer distant points of light, but accessible worlds waiting to be explored. And as we continue to push the boundaries of science and technology, the dream of interstellar travel through wormholes grows ever closer to reality. But before we can harness the power of wormholes, we first need to find them. Detecting these cosmic shortcuts is no easy task, and it requires a whole new approach to observing the universe. So, as we turn our attention to the next frontier, the challenges of detecting wormholes, we're reminded that the journey to unlocking the secrets of the cosmos is as thrilling as the destinations we might one day reach. If wormholes exist, how would we even begin to find them? Unlike black holes, which leave behind unmistakable signs of their presence, like the ripples in spacetime detected by LIGO or the glowing accretion disks captured by the Event Horizon Telescope, wormholes are far more elusive. They don't devour stars or spew jets of radiation. Instead, they're more like cosmic phantoms, hiding in plain sight, but that doesn't mean they're invisible. Scientists have proposed several ingenious methods to detect these spacetime shortcuts, each with its own set of challenges and possibilities. One promising approach is gravitational lensing. Just as a glass lens bends light to magnify distant objects, a wormhole's immense gravitational field could distort the light from stars and galaxies behind it. This distortion would create a unique pattern, a kind of cosmic fingerprint that astronomers could potentially spot. However, here's the catch. Black holes and other massive objects also produce gravitational lensing effects, making it tricky to distinguish a wormhole from, say, a supermassive black hole. As astrophysicist Kip Thorne explains, the key lies in the subtle differences in the lensing patterns, but teasing out those differences requires incredibly precise observations. Another potential clue comes from gamma-ray bursts, the most energetic explosions in the universe. Some theories suggest that if a wormhole were to collapse or interact with surrounding matter, it could produce a specific kind of gamma-ray signature. These bursts would be unlike anything we've seen before, offering a tantalizing hint of a wormhole's presence. Yet, even here, the challenge is immense. Gamma-ray bursts are rare and often originate from cataclysmic events like collapsing stars or merging neutron stars, so pinpointing a wormhole-related burst would require both luck and cutting-edge technology. Then there's the idea of looking for wormholes through their gravitational waves. Just as black hole mergers send ripples through spacetime, a wormhole could, in theory, produce its own unique gravitational wave signature. These ripples would carry information about the wormhole's shape, size, and even its stability, but detecting such signals would require advancements in gravitational wave observatories, pushing our current technology to its limits. As physicist Vitor Cardoso notes, wormholes, if they exist, would leave a distinct imprint on gravitational waves, but isolating that signal from the cosmic noise is like finding a whisper in a hurricane. Despite these challenges, the search for wormholes is far from hopeless. Advances in observational technology, from next-generation telescopes to more sensitive gravitational wave detectors, are bringing us closer than ever to uncovering these cosmic mysteries. And while we haven't found definitive proof of a wormhole yet, the search itself is driving innovation and deepening our understanding of the universe. As we explore these methods, it's worth reflecting on how much of science is about the journey, not just the destination. The quest to detect wormholes isn't just about finding shortcuts through space. It's about pushing the boundaries of what we know and challenging ourselves to see the universe in new ways. And as we turn our attention to the next frontier, how wormholes have captured the imagination of popular culture, we're reminded that sometimes the most profound discoveries begin with a spark of curiosity and a willingness to dream big. Wormholes have long been a staple of science fiction, capturing the imagination of audiences with their promise of instant travel across the cosmos. From the silver screen to the pages of novels, these theoretical tunnels through spacetime have been depicted in countless ways, shaping how we think about them and inspiring generations of dreamers. Take Christopher Nolan's Interstellar, for example. In this visually stunning film, a massive wormhole near Saturn becomes humanity's lifeline, offering a shortcut to distant star systems in search of a new home. The movie's portrayal of the wormhole, complete with its shimmering, spherical appearance, was grounded in real physics, thanks to the input of renowned physicist Kip Thorne. Yet it also took creative liberties, blending scientific accuracy with cinematic spectacle to create a compelling narrative. Then there's Star Trek, where wormholes, or subspace conduits, are a recurring element of the franchise. In episodes like Deep Space Nine, the Bajoran wormhole serves as a gateway to the unexplored Gamma Quadrant, opening up endless possibilities for exploration and conflict. Unlike Interstellar, Star Trek often treats wormholes as natural phenomena, existing without the need for exotic matter or advanced technology. This portrayal taps into the idea that the universe might already be threaded with these cosmic shortcuts, waiting to be discovered. Books have also played a significant role in popularizing wormholes. Carl Sagan's Contact introduced readers to the concept of a wormhole network created by an advanced alien civilization. The novel's protagonist, Ellie Arroway, travels through one of these tunnels, experiencing a journey that transcends space and time. Sagan's depiction was so influential that it inspired real scientific discussions about the feasibility of wormholes, proving that fiction can sometimes pave the way for scientific inquiry. But how do these portrayals affect our understanding of wormholes? For many, movies and TV shows are the first, and sometimes only exposure to these ideas. While they often simplify or exaggerate the science for dramatic effect, they also spark curiosity and interest. A viewer who watches Interstellar might find themselves asking questions about gravity, space-time, and the nature of the universe. In this way, popular culture acts as a bridge, connecting complex scientific concepts with a broader audience. At the same time, these depictions can also create misconceptions. The idea of wormholes as stable, easily navigable tunnels is a far cry from the reality of their theoretical instability and the immense challenges of creating or finding one. Yet, even these exaggerated portrayals have value. They encourage us to dream big, to imagine a future where the stars are within reach, and to consider the possibilities that lie beyond our current understanding. As we look to the future, it's fascinating to see how real science is beginning to catch up with these fictional ideas. From the ER=EPR conjecture to advances in quantum physics, the line between science and science fiction is becoming increasingly blurred. What once seemed like pure fantasy traveling through wormholes, exploring distant galaxies might one day be within our grasp. So, as we reflect on the role of wormholes in popular culture, we're reminded of the power of storytelling to shape our vision of the universe. Whether on screen or in print, these narratives inspire us to ask questions, seek answers, and push the boundaries of what's possible. And as we turn our attention to the next frontier, the ethical and philosophical questions raised by wormhole travel, we're reminded that the journey to the stars is as much about exploring the unknown within ourselves as it is about reaching distant worlds. The Fermi paradox has puzzled scientists and thinkers for decades. If the universe is so vast and filled with countless stars and planets, why haven't we encountered any signs of extraterrestrial life? It's a question that strikes at the heart of our search for cosmic companions, and it might just have a surprising connection to wormholes. Could these theoretical tunnels through spacetime hold the key to solving the paradox? One intriguing possibility is that advanced civilizations have already mastered wormhole travel, using these cosmic shortcuts to explore or even colonize the universe. If that's the case, why haven't we seen them? One explanation is that wormholes might be so efficient that these civilizations don't need to spread out across the galaxy in the traditional sense. Instead of building sprawling empires or leaving obvious markers of their presence, they could be quietly moving through wormholes, exploring vast distances without leaving a trace. Imagine a civilization so advanced that it treats the universe like a network of interconnected rooms, stepping through wormholes as effortlessly as we walk through doors. Another angle to consider is the sheer scale of the universe. Even with wormholes, the cosmos is unimaginably vast. It's possible that advanced civilizations are out there, but they're simply too far away for us to detect, or they're operating on timescales so vast that their existence doesn't overlap with ours. As physicist Stephen Webb once noted, the universe might be teeming with life, but the distances and timescales involved could make contact nearly impossible. Wormholes could be their solution to this problem, allowing them to bypass the limitations of space and time. But there's also a darker possibility. What if advanced civilizations avoid us intentionally? Some theories suggest that intelligent species might choose to remain hidden, either out of caution or because they've evolved beyond the need for physical expansion. In this scenario, wormholes could serve as a kind of cosmic cloaking device, enabling them to move unseen through the universe. It's a sobering thought, one that raises questions about our place in the cosmos and whether we're truly alone. These ideas don't just challenge our understanding of the Fermi paradox, they also highlight the profound implications of wormhole technology. If wormholes exist and can be harnessed, they could fundamentally alter how civilizations interact, or don't interact, with one another. They could explain why we haven't found evidence of extraterrestrial life, not because it isn't out there, but because it operates in ways we can't yet comprehend. As we ponder these possibilities, it's worth reflecting on what they mean for humanity. If wormholes are the key to unlocking the secrets of the universe, they could also hold the answers to some of our most profound questions. But with great power comes great responsibility, and the ethical implications of wormhole travel are as vast as the cosmos itself. This brings us to the next frontier, the ethical dilemmas raised by wormhole technology. What happens when we gain the ability to traverse the universe at will? How do we ensure that this power is used responsibly? These are the questions we'll explore as we delve into the moral dimensions of wormhole travel, a topic that challenges us to think not just about the science, but about the kind of future we want to create. As we stand on the brink of potentially unlocking wormhole technology, it's not just the science we need to consider, it's the ethics. Imagine a future where humanity has the ability to traverse the cosmos through these cosmic shortcuts. While the possibilities are thrilling, they also come with profound responsibilities. What happens if we encounter extraterrestrial life during our travels? How do we ensure that our actions don't inadvertently harm ecosystems or civilizations we know nothing about? These are the kinds of questions that make wormhole travel as much a moral challenge as a technical one. Take, for instance, the idea of encountering an alien species. If we were to step through a wormhole and find ourselves on a planet teeming with life, how would we approach it? Do we have the right to explore, colonize, or even study these beings? History has shown us the dangers of unchecked exploration, from the colonization of Earth's continents to the exploitation of indigenous peoples. If we're not careful, we risk repeating those mistakes on a cosmic scale. As astrobiologist David Grinspoon warns, the universe isn't just a playground for humanity, it's a shared space, and we need to approach it with humility and respect. Then there's the risk of contamination. Just as Earth's explorers once carried diseases to new lands, wormhole travelers could inadvertently introduce Earth's pathogens to alien ecosystems, or bring unknown extraterrestrial microbes back to our planet. The consequences could be catastrophic, not just for us, but for any life forms we encounter. This isn't just a hypothetical concern, it's a challenge that space agencies like NASA already grapple with when planning missions to places like Mars. The protocols we develop for wormhole travel would need to be even more rigorous, ensuring that we don't become interplanetary carriers of destruction. But the ethical dilemmas don't stop there. What if wormholes allow us to access resources on distant planets? The temptation to exploit these resources could lead to conflicts, both on Earth and beyond. Who gets to control these cosmic gateways? How do we prevent them from becoming tools of power and domination? These questions highlight the need for international cooperation and ethical frameworks that prioritize the well-being of all life, not just humanity's ambitions. At the same time, wormholes could also offer opportunities for collaboration and discovery. Imagine a future where humanity works alongside other intelligent species to explore the universe, sharing knowledge and resources. This vision of cosmic unity is inspiring, but it requires us to approach wormhole travel with a sense of responsibility and foresight. As philosopher Martha Nussbaum reminds us, ethics isn't just about what we can do, it's about what we should do, even when no one is watching. As we reflect on these challenges, it's clear that wormhole technology isn't just a scientific endeavor, it's a test of our values and our ability to think beyond ourselves. And while the road ahead is fraught with complexity, it's also filled with promise. By addressing these ethical questions now, we can lay the groundwork for a future where wormholes are not just gateways to the stars, but pathways to a more thoughtful and compassionate exploration of the cosmos. Now, as we turn our attention to the next frontier, we'll explore how artificial intelligence might play a pivotal role in unlocking the secrets of wormholes. From simulating exotic matter to navigating the complexities of spacetime, AI could be the key to making wormhole travel a reality. But with great power comes great responsibility, and the ethical questions we've just explored will only become more pressing as technology advances. So, let's dive deeper into the fascinating intersection of AI and wormhole research, and discover how these two fields could shape the future of space exploration. Artificial intelligence is revolutionizing nearly every field of science, and wormhole research is no exception. With its ability to process vast amounts of data and simulate complex scenarios, AI could be the key to unlocking the secrets of these cosmic shortcuts. Imagine an AI system sifting through decades of astrophysical data, searching for subtle patterns or anomalies that might hint at the presence of a wormhole. Or picture a supercomputer running simulations of spacetime, testing countless wormhole configurations to determine which ones could remain stable. These are just a few ways AI is poised to transform our understanding of wormholes, and potentially the universe itself. One of the most exciting applications of AI in this field is its ability to analyze gravitational wave data. Gravitational waves, ripples in spacetime caused by massive cosmic events, are incredibly faint and complex. Detecting them requires sifting through mountains of noise to find the faintest signals. As physicist Chiara Mingarelli explains, AI algorithms are uniquely suited for this task. They can process data at incredible speeds and identify patterns that might otherwise go unnoticed. This capability could be crucial in detecting the subtle signatures of wormholes, which, unlike black holes or neutron stars, don't produce obvious gravitational wave patterns. By training AI to recognize these unique signals, we might finally find evidence of wormholes hiding in the cosmos, but AI's role doesn't stop at detection. It could also help us design and test new wormhole theories. The equations governing wormholes are notoriously difficult to solve, often requiring supercomputers to model even the simplest scenarios. AI could take this a step further, exploring solutions that human researchers might never think to try. For example, some AI systems are already being used to generate novel mathematical models in physics, uncovering unexpected connections between seemingly unrelated concepts. As researcher Miles Cranmer puts it, AI doesn't just crunch numbers, it can inspire new ways of thinking about the universe. This potential extends to the search for exotic matter, the elusive substance needed to stabilize wormholes. AI-driven simulations could explore the properties of hypothetical materials, predicting how they might behave under extreme conditions. By narrowing down the possibilities, AI could help us identify the most promising candidates for creating or stabilizing wormholes, bringing us one step closer to turning theory into reality. Of course, the integration of AI into wormhole research isn't without its challenges. These systems require vast amounts of data to train effectively, and in the case of wormholes, much of that data is still theoretical. There's also the question of how to interpret the results. As astrophysicist Jana Levin notes, AI can provide us with incredible insights, but it's up to us to ask the right questions and understand the answers. Despite these hurdles, the potential for AI to accelerate wormhole research is immense. It's not just about finding shortcuts through space, it's about pushing the boundaries of what we know and exploring the deepest mysteries of the cosmos. And as we delve into these mysteries, we're also uncovering new questions. Could wormholes connect not just distant points in our universe, but entirely different universes? This idea, once the realm of science fiction, is now being taken seriously by physicists. As we turn our attention to the next frontier, the possibility of wormholes linking parallel universes, we're reminded that the universe is far stranger and more interconnected than we ever imagined. The journey to unlock its secrets is just beginning, and with AI as our guide, the possibilities are as vast as the cosmos itself. What if the universe we live in is just one of countless others, each with its own unique laws of physics and possibilities? This is the heart of the multiverse theory, a bold idea that suggests our cosmos is just one bubble in an infinite sea of universes. And here's the twist: wormholes might not just connect distant points in our universe, they could serve as gateways to these parallel realms. It's a concept that blurs the line between science and science fiction, but it's grounded in some of the most cutting-edge theories in physics. To understand how wormholes might link to parallel universes, let's start with the multiverse idea. According to some theories, our universe is part of a vast, interconnected network of universes, each existing in its own bubble of spacetime. These bubbles could be separated by unimaginable distances, or they might overlap in ways we can't perceive. Wormholes, with their ability to bridge spacetime, could theoretically connect these bubbles, creating pathways between universes. As physicist Brian Greene explains, if the multiverse exists, wormholes could be the threads that stitch it together, allowing travel not just through space, but between realities. But how plausible is this idea? One piece of the puzzle comes from string theory, which suggests that our universe might be a three-dimensional brane floating in a higher dimensional space. In this view, parallel universes could exist on separate branes, and wormholes might form where these branes intersect or overlap. Think of it like two sheets of paper floating side by side. If you fold them just right, you could poke a hole through both, creating a connection between the two surfaces. In the same way, wormholes might allow passage between brains and the universes they contain. Now, let's take this a step further with a thought experiment. Imagine you're standing in front of a wormhole that leads to a parallel universe. What would you see? Would the laws of physics there be the same as ours, or entirely different? Some theories suggest that parallel universes could have completely different constants of nature. Gravity might be stronger, light might travel slower, or even time itself might flow in reverse. Stepping through a wormhole into such a universe would be like entering a world where the rules of reality are rewritten. It's a dizzying prospect, but one that highlights the profound implications of wormholes as cosmic gateways. Of course, this raises as many questions as it answers. If wormholes can connect parallel universes, how do we ensure we're stepping into a universe where we can survive? What happens if the wormhole collapses while we're on the other side? These are the kinds of challenges that make the idea of multiverse travel as daunting as it is exciting. Yet, they also remind us of the incredible potential wormholes hold, not just for exploring our universe, but for redefining our understanding of reality itself. As we ponder these possibilities, it's worth considering how they connect to another cosmic mystery, dark energy. This enigmatic force, which drives the accelerated expansion of the universe, might play a crucial role in the stability and formation of wormholes. And as we'll explore next, understanding dark energy could be the key to unlocking the secrets of these cosmic shortcuts, and perhaps even the multiverse itself. Dark energy is one of the most mysterious forces in the universe, and its influence might extend far beyond the accelerating expansion of the cosmos. What if this enigmatic energy also plays a critical role in the stability of wormholes? At first glance, the connection might not seem obvious, but when we look closer, it reveals a fascinating interplay between the largest and smallest scales of the universe. Dark energy, which makes up about 68% of the universe, exerts a repulsive force that counteracts gravity, pushing galaxies apart at an ever-increasing rate. This same repulsive force could, in theory, help stabilize wormholes by counteracting the immense gravitational pull that would otherwise cause them to collapse. To understand this connection, let's break it down. Wormholes, as we've discussed, are tunnels through spacetime that require a delicate balance of forces to remain open. Gravity naturally tries to squeeze these tunnels shut, but exotic matter, or in this case, dark energy, could provide the necessary repulsive force to keep them stable. Imagine trying to hold open a doorway with a powerful spring pushing it closed. Dark energy could act like a counter spring, applying just the right amount of outward pressure to keep the doorway, or in this case, the wormhole open. This idea isn't just speculative, it's grounded in the equations of general relativity, which allow for the possibility of such a balance. But here's the catch: dark energy itself is still poorly understood. We know it exists because of its observable effects on the universe's expansion, but its true nature remains one of the biggest unsolved mysteries in physics. Is it a property of spacetime itself, as Einstein's cosmological constant suggests, or is it a dynamic field that changes over time, like some theories of quintessence propose? Without a clearer understanding of dark energy, it's difficult to say exactly how it might influence wormhole stability. As physicist Sean Carroll puts it, dark energy is the wild card of cosmology. Until we understand it better, we can only speculate about its role in phenomena like wormholes. Studying dark energy is no easy task. Unlike black holes or neutron stars, which emit detectable radiation, dark energy doesn't interact with light or matter in any obvious way. It's invisible, intangible, and seemingly everywhere, making it a challenge to measure directly. Current methods rely on observing its effects on the large-scale structure of the universe, such as the distribution of galaxies and the rate of cosmic expansion. But even with advanced telescopes and sophisticated models, dark energy remains elusive. This makes it all the more intriguing to consider its potential connection to wormholes, a concept that's equally shrouded in mystery. Despite these challenges, the idea of dark energy stabilizing wormholes opens up exciting possibilities. If dark energy can counteract gravity on a cosmic scale, could it also be harnessed to create or maintain wormholes? Some theories suggest that advanced civilizations might one day manipulate dark energy to engineer stable wormholes, turning them into practical gateways for interstellar travel. Others propose that naturally occurring wormholes could be anchored by regions of concentrated dark energy, creating a network of cosmic shortcuts hidden in plain sight. As we explore these ideas, it's worth reflecting on how much of the universe remains unknown. Dark energy, wormholes, and the mysteries they hold remind us that science is a journey of discovery, filled with questions that push the boundaries of our understanding. And just as dark energy might hold the key to wormhole stability, wormholes themselves could lead us to even greater cosmic revelations. This brings us to the next frontier, white holes. Often described as the opposite of black holes, these theoretical objects could be intimately connected to wormholes, offering a glimpse into the deeper mysteries of spacetime. What are white holes, and how do they fit into the puzzle of wormholes and the universe at large? Let's dive in and find out. If black holes are the cosmic vacuum cleaners of the universe, sucking in everything that crosses their event horizon, then white holes are their polar opposites, cosmic fountains, spewing out matter and energy instead of swallowing them. These theoretical objects are often described as the exit side of a wormhole, completing the cosmic tunnel that begins with a black hole. But while black holes have been observed and studied for decades, white holes remain purely hypothetical, existing only in the equations of physics. So, what exactly are white holes, and why do they matter in the quest to understand wormholes and the universe itself? Picture a black hole as a one-way street where everything enters but nothing escapes. A white hole, on the other hand, is like a one-way street in reverse. Nothing can enter, but matter and energy can pour out. If a black hole is a cosmic drain, a white hole is a cosmic spout. Together, they could form the two ends of a wormhole, with the black hole acting as the entrance and the white hole as the exit. This idea isn't just poetic, it's grounded in the mathematics of general relativity, which allows for such solutions to Einstein's equations. But why haven't we seen white holes? The answer lies in their nature. Unlike black holes, which form from the collapse of massive stars, white holes would require conditions that seem to defy the laws of physics as we know them. They'd need to spontaneously expel matter and energy without any obvious source, making them incredibly unstable. If they exist at all, one of the biggest challenges in studying white holes is their theoretical instability. While black holes are stable over cosmic timescales, white holes are thought to be fleeting, existing only for a fraction of a second before collapsing or transforming into something else. This makes them nearly impossible to observe directly. As physicist Carlo Rovelli explains, white holes are like ghosts in the equations of physics. They are there, but they're incredibly hard to pin down. Despite this, some researchers believe that white holes might not be entirely out of reach. For example, quantum gravity theories suggest that black holes could eventually transform into white holes, releasing the matter and energy they've consumed over billions of years. If true, this process could leave behind detectable signatures, offering a way to indirectly observe white holes. To make this concept more tangible, let's use a simple analogy. Imagine a hose with water flowing through it. If you pinch one end, water builds up pressure and eventually bursts out the other side. In this metaphor, the pinched end is the black hole and the burst is the white hole. The water represents matter and energy flowing through the wormhole, connecting the two ends. While this analogy simplifies a complex idea, it helps illustrate how white holes could serve as the output for wormholes, releasing what the black hole input has swallowed. But what does this mean for wormhole travel? If white holes are the exit points for wormholes, they could play a crucial role in ensuring safe passage through these cosmic tunnels. Instead of emerging into the heart of a collapsing star or the void of empty space, travelers might step out of a white hole into a stable, hospitable region of the universe. This idea isn't just science fiction. It's a serious area of study in theoretical physics. Some models even suggest that white holes could emit bursts of radiation or particles, creating observable signals that could help us locate wormholes hidden in the cosmos. As we explore these ideas, it's worth considering how white holes fit into the larger picture of spacetime and the universe. They remind us that the cosmos is full of symmetries and opposites, from black holes and white holes to matter and antimatter. These dualities challenge us to think beyond the limits of our current understanding and imagine new possibilities for how the universe works. Now, as we turn our attention to the next frontier, let's explore how wormholes might revolutionize not just travel, but communication across the cosmos. Imagine sending a message through a wormhole, bypassing the vast distances of space to connect with civilizations light years away. This idea isn't just a pipe dream. It's a tantalizing possibility that could redefine how we share knowledge and ideas across the stars. Imagine a future where messages travel faster than light, bridging the gap between stars in the blink of an eye. This isn't just a dream, it's the potential of wormholes as cosmic communication channels. While we often think of wormholes as shortcuts for physical travel, they could also revolutionize how we share information across the universe. By transmitting data through these space-time tunnels, civilizations separated by light years could communicate instantly, bypassing the frustrating delays imposed by the speed of light. But how feasible is this idea, and what would it take to turn it into reality? The concept hinges on the idea that wormholes could act as conduits for information, much like fiber optic cables on Earth. Instead of sending signals across vast distances of space, we'd route them through a wormhole, effectively creating a cosmic version of the Internet. This would require a stable, traversable wormhole, of course, as well as a way to encode and decode information at each end. But if we could overcome these challenges, the implications would be staggering. Imagine sending a message to a colony on Proxima Centauri and receiving a reply in real time, or collaborating with an alien civilization on scientific discoveries without waiting centuries for a response. Theoretical physics offers some intriguing possibilities here. One idea, known as quantum entanglement communication, suggests that particles linked by entanglement could transmit information instantaneously, even across wormholes. While this is still speculative, it's grounded in the same principles that make wormholes possible in the first place. As physicist Leonard Susskind explains, if wormholes are the highways of spacetime, then quantum entanglement could be the traffic signals guiding information through the network. But the challenges are immense. For one, wormholes are notoriously unstable, and keeping them open long enough to transmit information would require exotic matter or energy on a scale we can't yet imagine. There's also the question of how to encode information in a way that survives the journey through a wormhole. Gravitational forces, radiation, and other cosmic phenomena could distort or destroy signals, making reliable communication difficult. And let's not forget the ethical considerations. What happens if we accidentally transmit harmful information, or if our messages fall into the wrong hands? Despite these hurdles, the idea of wormhole communication is too compelling to ignore. It represents a new frontier in our understanding of the universe, one where distance and time no longer limit our ability to connect. And as we explore this possibility, we're also uncovering deeper questions about the nature of information itself. Could wormholes reveal new ways to encode, transmit, and store knowledge, not just across space but across time? This brings us to the next frontier, the role of wormholes in the early universe. What if these cosmic tunnels weren't just tools for the future, but relics of the past, formed in the fiery chaos of the Big Bang? As we delve into this idea, we'll explore how wormholes might have shaped the cosmos in its infancy, and what they could tell us about the origins of everything. What if the universe's very first moments were shaped by wormholes? This might sound like a far-out idea, but it's one that some cosmologists are taking seriously. As we peer back in time to the Big Bang, the universe was a seething cauldron of energy and matter, packed into an unimaginably dense and hot state. In that chaos, spacetime itself might have been riddled with tiny, fleeting wormholes, cosmic shortcuts that could have played a crucial role in shaping the universe as we know it today. One of the most intriguing theories suggests that wormholes could have been instrumental during cosmic inflation, the rapid expansion of the universe that occurred just fractions of a second after the Big Bang. During this brief but explosive period, the universe ballooned in size, stretching from smaller than an atom to something far larger than our observable cosmos. But what drove this expansion? While the leading explanation involves a mysterious form of energy called the inflaton field, some researchers propose that wormholes could have contributed to this process. As cosmologist Alan Guth, one of the pioneers of inflation theory, puts it, the early universe was a place of extreme conditions where the rules of physics as we know them were stretched to their limits. Wormholes, if they existed, could have been part of that cosmic dance. How might this have worked? Imagine the early universe as a bubbling soup of space-time, constantly warping and twisting under extreme pressures. In such an environment, microscopic wormholes could have formed spontaneously, acting like cosmic pressure valves. These wormholes might have allowed energy and matter to flow between different regions of the universe, smoothing out irregularities and driving the rapid expansion we see evidence of today. It's a bit like how air flows through tiny holes in a balloon, helping it expand evenly. In this scenario, wormholes wouldn't just be cosmic shortcuts, they'd be cosmic architects, helping to shape the universe's structure on the grandest scales. But the implications don't stop there. If wormholes were present in the early universe, they might have left behind subtle fingerprints in the cosmic microwave background, the faint afterglow of the Big Bang. These imprints could provide clues about the universe's infancy, offering a window into a time when the cosmos was still taking shape. While no definitive evidence has been found yet, the idea has sparked intense interest among cosmologists. As physicist Lisa Randall explains, Wormholes in the early universe are a tantalizing possibility. They could help us solve some of the deepest mysteries in cosmology, from the nature of inflation to the origins of dark matter. This theory also raises fascinating questions about the nature of spacetime itself. If wormholes were present at the birth of the universe, could they still exist today, hidden in the fabric of reality? And if so, could they offer clues about the universe's ultimate fate? These are the kinds of questions that keep cosmologists up at night, and they remind us that the universe is far stranger and more interconnected than we ever imagined. As we ponder the role of wormholes in the early universe, we're reminded that the cosmos is a story still being written, one filled with twists, turns, and surprises at every corner. And just as wormholes might have shaped the universe's beginnings, they could also hold the key to understanding its future. But the mysteries don't end there. If wormholes were present in the early universe, they might have been part of an even more fundamental structure, something known as quantum foam. This concept, which suggests that spacetime is frothy and chaotic at the smallest scales, could provide the missing link between wormholes and the quantum world. So, as we dive into the next frontier, let's explore how this quantum foam might rewrite our understanding of the universe, and perhaps even reality itself. At the smallest scales imaginable, the fabric of spacetime isn't smooth and continuous, it's a bubbling, frothy chaos known as quantum foam. This isn't just a poetic description, it's a theoretical framework that suggests spacetime itself is made up of tiny, fluctuating structures, constantly forming and dissolving at scales so small they're almost impossible to comprehend. To put it simply, if you could zoom in far enough, spacetime wouldn't look like a calm ocean. It would resemble a boiling pot of water with bubbles popping in and out of existence. And here's where things get even more fascinating. Some of these bubbles might actually be microscopic wormholes, appearing and vanishing in the blink of an eye. To visualize this, think of quantum foam as a cosmic version of the static you see on an old TV screen. Each flicker of static represents a tiny fluctuation in spacetime, and every so often, one of those flickers could be a wormhole, a fleeting connection between 2 points in the universe. These wormholes wouldn't be the massive, traversable tunnels we often imagine. They'd be incredibly small, existing only for fractions of a second before collapsing back into the quantum foam. But their fleeting existence could have profound implications for our understanding of the universe. The idea of quantum foam isn't just speculative, it's rooted in the principles of quantum mechanics and general relativity. At these minuscule scales, the laws of physics as we know them begin to break down. Gravity and quantum forces interact in unpredictable ways, creating a turbulent sea of spacetime fluctuations. As physicist John Wheeler, who first proposed the concept, famously said, "The universe is not only stranger than we imagine, but stranger than we can imagine." Quantum foam embodies this strangeness, pushing the boundaries of what we thought was possible. But studying quantum foam is no easy task. These structures are unimaginably small, existing at scales trillions of times smaller than an atom. Our current technology is nowhere near capable of observing them directly, so scientists rely on mathematical models and theoretical frameworks to explore their properties. Even then, the calculations are incredibly complex, involving a delicate interplay between quantum mechanics and the curvature of spacetime. It's like trying to map the surface of a stormy ocean using only the faintest ripples on its surface. Despite these challenges, the concept of quantum foam has opened up exciting new avenues for research. For instance, Some theories suggest that these microscopic wormholes could play a role in the behavior of black holes or even the early universe's rapid expansion. Others propose that they might be linked to the mysterious phenomenon of dark energy, which drives the universe's accelerating expansion. If true, this would mean that the smallest structures in the universe could hold the key to understanding its largest mysteries. Now, let's take this idea a step further. If quantum foam contains microscopic wormholes, could we one day harness them for practical purposes? Imagine tapping into these fleeting tunnels to extract energy or transmit information across vast distances. It's a bold idea, but one that's grounded in the same principles that make quantum foam so intriguing. The energy locked within these tiny fluctuations could, in theory, be immense, if only we could find a way to access it. This brings us to the next frontier, the possibility of using wormholes for energy extraction. Could these cosmic shortcuts not only revolutionize travel and communication, but also provide a new source of energy for humanity? The answer might lie in the very fabric of spacetime itself. So, as we dive into the next section, let's explore how wormholes could unlock a universe of energy and what it would take to harness it. What if the key to unlocking a virtually limitless energy source lies not in the stars, but in the fabric of spacetime itself? This is the tantalizing possibility of wormholes as cosmic power plants, a concept that pushes the boundaries of theoretical physics and our imagination. While wormholes are often discussed as shortcuts for travel or communication, their potential as energy sources is equally groundbreaking. Imagine tapping into the immense gravitational forces and exotic matter that stabilize these space-time tunnels to generate power on an unprecedented scale. For advanced civilizations, this could be the ultimate energy solution, far surpassing anything we've achieved with nuclear fusion, solar panels, or fossil fuels. The scientific basis for this idea lies in the unique properties of wormholes. To keep a wormhole open, you need exotic matter with negative energy density, a substance that exerts a repulsive force, counteracting the immense gravitational pull that would otherwise collapse the tunnel. This exotic matter isn't just a theoretical curiosity, it's a potential gold mine of energy. If we could find a way to harness or even replicate it, the energy output could be staggering. As physicist Michio Kaku explains, wormholes aren't just gateways through space, they're reservoirs of energy waiting to be tapped. The challenge is figuring out how to access them without destabilizing the entire structure. One approach involves the concept of vacuum energy, the quantum fluctuations that permeate empty space. These fluctuations are thought to contain vast amounts of energy, and some theories suggest that wormholes could act as conduits, channeling this energy into a usable form. It's a bit like drilling into an underground reservoir, except the reservoir is the fabric of space-time itself. Of course, this is easier said than done. The energy locked within a wormhole is immense, but extracting it would require technology far beyond our current capabilities. We'd need to find a way to safely interact with exotic matter, stabilize the wormhole long enough to extract energy, and then convert that energy into a usable form, all without triggering a catastrophic collapse. To put this into perspective, let's consider a simple analogy. Imagine a dam holding back a massive reservoir of water. The water represents the energy contained within a wormhole, and the dam is the exotic matter keeping it stable. To extract the energy, you'd need to carefully release the water through turbines, generating power without breaking the dam. In the case of a wormhole, the turbines would be some form of advanced technology capable of converting space-time fluctuations into usable energy. It's a delicate balancing act, one that would require a deep understanding of both quantum mechanics and general relativity. But what makes this idea so compelling isn't just the potential for limitless energy, it's the implications for humanity's future. If we could harness wormhole energy, it could revolutionize everything from space travel to global power grids. Imagine spacecraft powered by wormhole-derived energy, capable of traveling vast distances without the need for massive fuel reserves. Or think of cities powered by clean, sustainable energy extracted from the fabric of spacetime itself. The possibilities are as vast as the universe, and they challenge us to rethink what's possible in the realm of energy production. Of course, the challenges are immense. We're still far from understanding how to stabilize wormholes, let alone extract energy from them, and even if we could, there are ethical and practical considerations to address. How do we ensure that extracting energy from a wormhole doesn't destabilize it or cause unintended consequences? What happens if the energy source is finite and we deplete it? These are questions that scientists and ethicists will need to grapple with as we explore this bold new frontier. As we ponder these possibilities, it's worth reflecting on how much of the universe remains untapped. Wormholes, with their immense potential for energy, travel, and communication, remind us that the cosmos is full of surprises, and that the journey to unlock its secrets is just beginning. This brings us to the next frontier, the role of wormholes in solving some of the universe's greatest mysteries. From the nature of dark matter to the origins of the Big Bang, wormholes could be the key to unraveling the deepest puzzles of the cosmos. So, let's dive into how these cosmic shortcuts might help us decode the universe itself. What if the key to unraveling one of the universe's greatest mysteries, dark matter, lies hidden within the fabric of spacetime itself? Wormholes, those elusive cosmic shortcuts, might hold the answer. Dark matter, the invisible substance that makes up about 27% of the universe, has baffled scientists for decades. We know it exists because of its gravitational effects on galaxies and galaxy clusters, but we've never directly observed it. Could wormholes provide a missing link, offering clues about the nature of this enigmatic material? The connection between wormholes and dark matter isn't as far-fetched as it might seem. Some theories suggest that dark matter could be concentrated around wormholes, acting as a kind of cosmic glue that helps stabilize these spacetime tunnels. If true, this would mean that wormholes aren't just theoretical curiosities, they could be intertwined with the very structure of the universe. As astrophysicist Priyamvada Natarajan explains, wormholes and dark matter might be two sides of the same coin. Understanding one could lead us to a deeper understanding of the other. To grasp this idea, let's consider how dark matter behaves. Unlike ordinary matter, which interacts with light and other forms of radiation, dark matter is invisible and only interacts through gravity. This makes it incredibly difficult to detect directly. However, if dark matter clusters around wormholes, its gravitational influence could create subtle distortions in spacetime that we might be able to observe. Think of it like ripples on the surface of a pond. While the water itself is invisible, the ripples reveal its presence. In the same way, the gravitational effects of dark matter around wormholes could leave behind detectable signatures, offering a new way to study this mysterious substance. One intriguing possibility is that dark matter could be made up of particles that interact with wormholes in unique ways. For instance, some theories propose that dark matter particles might be able to traverse wormholes, effectively disappearing from one region of the universe and reappearing in another. This could explain why dark matter is so elusive it might not just be hiding in plain sight. It could be slipping through cosmic shortcuts that we can't yet detect. As physicist Lisa Randall puts it, dark matter's behavior might be less about what it is and more about where it goes. Wormholes could be the key to unlocking this puzzle. This idea also has profound implications for astrophysics. If wormholes and dark matter are connected, it could reshape our understanding of galaxy formation, cosmic structure, and even the evolution of the universe. For example, the distribution of dark matter in galaxies might be influenced by the presence of wormholes, creating patterns that we've yet to fully understand. By studying these patterns, we might uncover new insights into how dark matter shapes the cosmos and how wormholes fit into the bigger picture. While the connection between wormholes and dark matter is still speculative, it's a compelling area of research that's gaining traction among scientists. As we continue to explore this idea, we're reminded that the universe is full of hidden connections, waiting to be uncovered. And just as wormholes might shed light on dark matter, they could also lead us to an even more astonishing possibility: the existence of wormhole networks. Imagine a vast web of interconnected wormholes, spanning galaxies and even universes, with dark matter acting as the invisible threads that hold it all together. This is the frontier we'll explore next, a cosmic network that could redefine our understanding of space, time, and the very fabric of reality. So, let's dive deeper and see how these ideas are shaping the future of astrophysics. Imagine a universe where vast distances are no longer an obstacle, a cosmos crisscrossed with wormholes, forming an intricate network of cosmic highways. These aren't just isolated tunnels, they're a web of interconnected pathways linking stars, galaxies, and perhaps even universes. This is the vision of a wormhole network, a system that could revolutionize how we explore and navigate the cosmos. But how would such a network work, and what would it take to build and maintain it? To grasp this idea, think of the wormhole network as an interstellar subway system. Just as subway lines connect different parts of a city, wormholes could link distant points in the universe, creating a rapid transit system for spacecraft, information, and even civilizations. Each wormhole would act as a station, funneling travelers from one location to another almost instantaneously. The beauty of this system lies in its efficiency. Instead of spending centuries traveling between stars, we could hop from one wormhole to the next, traversing the galaxy in the time it takes to commute across a city. But constructing such a network is no small feat. One of the biggest challenges is stability. As we've discussed, wormholes are notoriously unstable, prone to collapsing under their own gravitational forces. To keep them open, we'd need a steady supply of exotic matter or some other form of negative energy, neither of which we've yet discovered. Even if we could source these materials, the logistics of deploying them across vast cosmic distances would be staggering. It's like trying to build a network of bridges across an ocean, except the ocean is constantly shifting, and the bridges are made of materials we've never seen before. Another hurdle is navigation. In a wormhole network, each tunnel would need to be precisely mapped and controlled to ensure safe passage. One wrong turn could send travelers hurtling into a collapsing wormhole or dumping them into the void of empty space. To avoid these dangers, we'd need advanced technology capable of monitoring and stabilizing the network in real time. Think of it as a cosmic air traffic control system, but one that operates on a scale far beyond anything we've ever attempted. Despite these challenges, the potential rewards are immense. A wormhole network could unite distant civilizations, fostering collaboration and exchange on a galactic scale. It could make interstellar trade a reality, allowing resources and ideas to flow freely across the cosmos, and it could open up new frontiers for exploration, turning the universe into a playground for discovery rather than a vast, insurmountable expanse. To bring this idea to life, let's use a visual analogy. Picture the universe as a sprawling city with stars and galaxies as neighborhoods. Without wormholes, traveling from one neighborhood to another would be like walking across the entire city, time-consuming and exhausting. But with a wormhole network, it's like having a subway system that connects every neighborhood, making the city feel smaller, more accessible, and infinitely more interconnected. Now, imagine adding another layer to this network, time synchronization. Just as wormholes could connect distant points in space, they might also link different moments in time. This brings us to the next frontier, the possibility of using wormholes not just for travel, but for coordinating events across the universe. It's a concept that blurs the line between space and time, challenging us to rethink how we understand both. So, as we turn our attention to the role of wormholes in time synchronization, we're reminded that the universe is full of surprises waiting to be uncovered. Imagine trying to coordinate a meeting with someone on the other side of the galaxy. Even if you could send messages at the speed of light, the delays would make real-time communication impossible. But what if wormholes could change that? What if these cosmic shortcuts could synchronize time across vast distances, allowing civilizations to interact as if they were in the same room? This is the intriguing possibility of wormholes as tools for time synchronization, a concept that could revolutionize not just travel, but the very way we connect across the cosmos. To understand how this might work, let's start with the basics of relativity. According to Einstein's theory, time isn't constant. It flows differently depending on gravity and velocity. This means that a clock on a fast-moving spacecraft will tick slower than one on Earth, a phenomenon known as time dilation. Over interstellar distances, these differences can add up, making it nearly impossible to coordinate events across the universe. But wormholes, with their ability to bend spacetime, could offer a solution. By linking two distant points, a wormhole could create a shared timeline, effectively synchronizing clocks across vast cosmic distances. Here's a thought experiment to illustrate this idea. Imagine two friends, Alice and Bob, living on opposite sides of the Milky Way. Without a wormhole, it would take tens of thousands of years for a message from Alice to reach Bob, and vice versa. But if a wormhole connects their worlds, Alice could send a message through the tunnel, and Bob would receive it almost instantly. Even more fascinating, if the wormhole's ends are synchronized, Alice and Bob could experience time in the same way, despite being light years apart. It's like having a cosmic Zoom call, where everyone's clocks are perfectly aligned. The scientific basis for this idea lies in the concept of closed, time-like curves, paths through spacetime that loop back on themselves. If a wormhole's two ends are synchronized, they could create a closed loop where time flows consistently between them. This wouldn't just solve the problem of communication delays. It could also enable real-time collaboration across the universe. Imagine scientists on different planets working together on experiments, or civilizations sharing knowledge and culture without the frustration of waiting centuries for a reply. But as with all things wormhole-related, there are challenges. Synchronizing time across a wormhole would require precise control over its structure and stability. Any fluctuations in the wormhole's geometry or energy could disrupt the timeline, causing confusion or even paradoxes. And then there's the question of how to create and maintain such a synchronized wormhole in the first place. Would it require advanced technology, exotic matter, or perhaps a deeper understanding of the quantum nature of spacetime? Despite these hurdles, the idea of time synchronization through wormholes is more than just a theoretical curiosity. It's a glimpse into a future where distance and time no longer limit our ability to connect. It challenges us to rethink how we understand communication, collaboration, and even the nature of time itself. This brings us to the next frontier, the role of wormholes in solving one of the most perplexing puzzles in physics, the information paradox. How can wormholes help us understand what happens to information that falls into a black hole? The answer might lie in the strange and mysterious connections between wormholes, black holes, and the quantum world. Let's explore this fascinating intersection next. What happens to information that falls into a black hole? It's a question that has baffled physicists for decades, sparking debates and challenging our understanding of the universe. According to quantum mechanics, information can never be destroyed. It's a fundamental law of nature, but black holes, with their immense gravitational pull, seem to defy this rule, swallowing everything that crosses their event horizon, including information. This contradiction, known as the black hole information paradox, has been one of the most perplexing puzzles in modern physics. Enter wormholes, the theoretical tunnels through spacetime that might hold the key to solving this mystery. The idea that wormholes could resolve the information paradox stems from the concept of quantum entanglement and the holographic principle. Imagine a black hole as a cosmic shredder, tearing apart anything that enters it. But what if the information isn't lost? What if it's simply transported somewhere else, like through a wormhole? This is the essence of the ER=EPR conjecture, which suggests that entangled particles like those that fall into a black hole are connected by microscopic wormholes. As physicist Leonard Susskind explains, wormholes might not just be cosmic shortcuts, they could be the universe's way of preserving information, ensuring that nothing is ever truly lost. To understand this better, let's break it down. When matter falls into a black hole, it's crushed into an infinitely dense point called a singularity. According to classical physics, the information about that matter, its composition, energy, and other properties is effectively erased. But quantum mechanics tells us that information can't be destroyed, it can only be scrambled or hidden. Wormholes offer a way to reconcile these two conflicting ideas. Instead of being lost, the information could be encoded on the surface of the black hole's event horizon, or even transported through a wormhole to another part of the universe. This concept has profound implications for our understanding of black holes and the nature of reality itself. If wormholes are the conduits for preserving information, they could act as cosmic data backups, ensuring that the universe's memory is never erased. It's a bit like deleting a file on your computer. It might seem gone, but traces of it still exist in the system. In the case of black holes, wormholes could be the hidden pathways that keep the universe's information intact, even when it seems to vanish into the void. But the implications go even deeper. If wormholes are linked to the preservation of information, they could also play a role in the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. This idea, first proposed by physicist Gerard T. Hooft and later expanded by Susskind, has reshaped how we think about spacetime and gravity. Wormholes could be the physical manifestation of this principle, acting as the threads that weave together the universe's information into a cohesive whole. As we explore these ideas, it's worth reflecting on how much of the universe remains shrouded in mystery. The black hole information paradox is just one piece of the puzzle, but it's a piece that could reshape our understanding of reality. And while wormholes offer a tantalizing solution, they also raise new questions. How do these cosmic shortcuts store and transmit information? Could we one day harness them to recover lost data from black holes? These are the kinds of challenges that keep physicists up at night, pushing the boundaries of what we thought was possible. But solving the information paradox isn't just about understanding black holes, it's about unlocking the secrets of spacetime itself. And as we turn our attention to the next frontier, we'll explore how stabilizing wormholes could bring us closer to turning these theoretical ideas into practical realities. What would it take to keep a wormhole open long enough to preserve information or even travel through it? The answer lies in the delicate balance of forces that govern these cosmic tunnels, a topic that's as fascinating as it is complex. So, let's dive into the science of wormhole stabilization and uncover what it might take to make these cosmic shortcuts a reality. What if the key to unlocking wormholes lies not just in understanding the fabric of spacetime, but in developing the technologies to manipulate it? Stabilizing a wormhole, keeping its tunnel open and navigable, is one of the most daunting challenges in theoretical physics. Without some form of exotic technology, these cosmic shortcuts would collapse almost instantly, making them useless for travel or communication. So, what kinds of technologies might we need to stabilize a wormhole, and how close are we to making them a reality? First, let's talk about energy. Stabilizing a wormhole requires counteracting the immense gravitational forces trying to squeeze it shut. This means we'd need an energy source capable of generating the equivalent of negative energy density, a substance that pushes outward instead of pulling inward. One possibility is harnessing the power of vacuum energy, the quantum fluctuations that permeate empty space. These fluctuations are thought to contain vast amounts of energy, and some theories suggest that advanced civilizations might one day tap into this resource to stabilize wormholes. Imagine a future where we've mastered the art of extracting energy from the fabric of spacetime itself, using it to power not just wormholes, but entire civilizations. But energy alone isn't enough. We'd also need advanced computing power to model and control the complex dynamics of a wormhole. Quantum computers, with their ability to perform calculations at speeds far beyond our current capabilities, could be the key. These machines wouldn't just crunch numbers, they'd simulate the behavior of spacetime, testing countless configurations to find the most stable wormhole designs. As physicist Seth Lloyd puts it, quantum computers could be the ultimate tools for exploring the universe, allowing us to solve problems that are currently beyond our reach. Of course, developing these technologies is no small feat. Quantum computers are still in their infancy, and harnessing vacuum energy remains a distant dream. Even if we could overcome these hurdles, there's the question of how to deploy these technologies on a cosmic scale. Stabilizing a wormhole wouldn't just require energy and computing power, it would demand precision engineering and materials science far beyond what we have today. It's like trying to build a bridge across a chasm, except the chasm is constantly shifting, and the bridge is made of materials we've never seen before. Despite these challenges, the potential rewards are immense. Stabilized wormholes could revolutionize not just space travel, but the way we think about the universe. They could open up new frontiers for exploration, turning the cosmos into a network of interconnected pathways. And as we'll explore next, these pathways could also transform the way we trade, share resources, and connect across the stars. So, what might interstellar trade look like in a universe crisscrossed by wormholes? Imagine a future where goods and ideas flow freely between distant worlds, unhindered by the vast distances of space. Wormholes could serve as the ultimate trade routes, linking civilizations in a cosmic economy that spans galaxies. It's a vision that challenges us to think beyond the limits of our current technology and to imagine a future where the stars are not just destinations, but partners in a shared journey. As we delve deeper into these ideas, we're reminded that the journey to unlock the secrets of wormholes is as much about innovation as it is about imagination. And while the road ahead is filled with challenges, the possibilities are as vast as the universe itself. So, let's turn our attention to the next frontier, how wormholes could redefine interstellar trade and create a new era of cosmic collaboration. Imagine a future where the vast distances of space no longer hinder trade, where goods, resources, and ideas flow freely between civilizations separated by light years. This isn't just a dream, it's the potential of wormholes as the backbone of a cosmic economy. By creating stable, traversable wormholes, we could establish interstellar trade routes that connect distant worlds, transforming the way civilizations interact and share resources. Picture a galaxy where planets specialize in producing unique goods, rare minerals from one world, advanced technology from another, and agricultural abundance from a third, all seamlessly exchanged through wormholes. The implications are staggering, a thriving network of commerce that transcends the limitations of space and time. But how would this work in practice? Let's break it down. First, wormholes would act as the ultimate trade highways, linking planets and star systems in a way that makes interstellar shipping as routine as air freight is today. Instead of waiting decades or centuries for cargo to arrive, goods could be transported almost instantly, allowing civilizations to share resources and knowledge in real time. For example, a planet rich in rare metals could trade with a world that excels in renewable energy technology, creating a symbiotic relationship that benefits both. This kind of interstellar trade wouldn't just boost economies, it could foster cultural exchange, scientific collaboration, and even political alliances on a galactic scale. Of course, the challenges are immense. Establishing and maintaining a wormhole trade network would require unprecedented levels of cooperation and technological sophistication. Each wormhole would need to be stabilized with exotic matter or energy, a task that's far beyond our current capabilities. There's also the question of who controls these cosmic gateways. Would they be owned by individual civilizations, governed by a galactic federation, or left open as shared resources for all? The potential for conflict over wormhole access is high, raising ethical and logistical questions that would need to be addressed. Another hurdle is the sheer scale of logistics involved. Interstellar trade would require standardized systems for tracking cargo, ensuring quality control, and resolving disputes across vast distances. Imagine trying to enforce trade agreements between civilizations that might not even share the same concept of time or currency. It's a challenge that would demand not just advanced technology, but also a new framework for interstellar diplomacy and governance. Despite these challenges, the idea of a cosmic economy is too compelling to ignore. The benefits: access to new resources, the spread of knowledge, and the potential for peaceful collaboration are immense. And as we explore these possibilities, we're reminded that wormholes aren't just tools for travel, they're pathways to a more interconnected and prosperous future. This brings us to the next frontier, the role of wormholes in addressing one of the universe's most profound challenges, the heat death. As the cosmos expands and cools, could wormholes offer a way to preserve energy and sustain life on cosmic timescales? The answer might lie in the strange and mysterious connections between wormholes, entropy, and the fate of the universe itself. Let's dive into this fascinating topic and uncover how wormholes could hold the key to solving the heat death of the universe. The heat death of the universe, it sounds like the ultimate cosmic finale, doesn't it? This bleak scenario, predicted by the laws of thermodynamics, suggests that as the universe expands and cools, all energy will eventually spread so thin that stars will burn out, galaxies will fade, and the cosmos will descend into a state of maximum entropy where nothing can happen. It's a chilling thought, but what if wormholes could offer a way to cheat this fate? What if these cosmic shortcuts could provide a lifeline, preserving energy and sustaining life long after the stars have dimmed? At the heart of this idea lies the concept of entropy, a measure of disorder in the universe. As entropy increases, usable energy decreases, leading to the heat death scenario. But wormholes, with their ability to bend and manipulate spacetime, might offer a way to counteract this process. Some theories suggest that wormholes could act as cosmic energy recyclers, funneling energy from one part of the universe to another, effectively delaying the inevitable. As cosmologist Sean Carroll puts it, wormholes could be the universe's way of keeping the lights on, even as entropy tries to turn them off. To visualize this, think of the universe as a giant game of cosmic billiards. Over time, the balls representing energy spread out, making it harder to score points, but a wormhole could act like a trick shot, redirecting the balls back into play. By connecting regions of the universe with differing energy densities, wormholes might allow energy to flow from areas of high concentration to those running low, creating a kind of cosmic balance that staves off heat death. It's a bold idea, but one that's grounded in the equations of general relativity and quantum mechanics. Of course, this raises a host of questions. How would we create or harness such wormholes? Could they operate on a scale large enough to impact the entire universe? And even if they could, would they buy us enough time to find a more permanent solution? These are the kinds of challenges that keep cosmologists up at night, but they also highlight the extraordinary potential of wormholes as tools for cosmic survival. As we consider these possibilities, it's worth reflecting on what they mean for our understanding of the universe. Wormholes aren't just shortcuts through space, they're potential lifelines, offering hope in the face of entropy's relentless march. And while the heat death of the universe might still be billions of years away, the journey to uncover its mysteries is one that pushes the boundaries of science and imagination. Now, as we turn our attention to the next frontier, let's explore a phenomenon that's just as mind-bending as wormholes themselves: wormhole time dilation. What happens when time flows differently at each end of a wormhole, and how could this strange effect reshape our understanding of space, time, and reality? The answers might just take us to the very edge of what we thought was possible. Imagine stepping through a wormhole and emerging not just in another part of the universe, but in a completely different moment in time. This isn't just the stuff of science fiction, it's a real possibility rooted in the physics of wormholes and the strange effects of time dilation. At its core, time dilation is a phenomenon where time flows at different rates depending on gravity and velocity. Near a black hole or at near light speeds, time slows down relative to everything else. Now, apply this to a wormhole. If one end of the tunnel is moving at high speed or exposed to intense gravity, time would pass more slowly there than at the other end. The result, a wormhole could become a time machine, linking not just distant points in space, but different moments in time. To make this more tangible, let's use a thought experiment. Picture a wormhole with one end placed near a black hole, where gravity is so strong that time slows to a crawl. If you were to step into the end of the wormhole far from the black hole, you'd emerge near the black hole's event horizon, but at a point in time that's earlier than when you entered. It's like walking through a door and coming out before you even stepped in. This isn't just a fun mental exercise. It's a scenario that's mathematically allowed by Einstein's equations of general relativity. As physicist Kip Thorne famously proposed, such a wormhole could serve as a practical time machine, allowing travel to the past or future. But here's the catch. Time dilation within a wormhole doesn't just open the door to time travel, it also raises profound questions about causality and the nature of time itself. What happens if you step through a wormhole and accidentally prevent your own birth, or alter a historical event in a way that changes the course of civilization? These paradoxes aren't just hypothetical, they challenge our understanding of how time works and whether the past, present, and future are as fixed as they seem. The scientific basis for wormhole time dilation lies in the interplay between gravity and spacetime. According to general relativity, massive objects like black holes warp spacetime, creating regions where time slows down. If a wormhole's ends are placed in areas with different gravitational strengths or velocities, time would flow at different rates at each end. This creates a time difference, a kind of temporal offset, that could be exploited for time travel. But as with all things wormhole-related, there's a catch. Stabilizing the wormhole long enough to use it as a time machine would require exotic matter or energy, something we've yet to discover or create. Another intriguing possibility is that wormhole time dilation could extend lifespans. Imagine a civilization that uses wormholes to send its citizens into the future, effectively allowing them to skip over long periods of time. A person could step into a wormhole, emerge decades or even centuries later, and experience a future society that's advanced far beyond their own. It's a concept that blurs the line between science and philosophy, challenging us to rethink what it means to live, age, and exist across time. As we explore these ideas, it's worth reflecting on how they might reshape not just our understanding of the universe, but also our place within it. Wormholes aren't just cosmic shortcuts, they're windows into the deeper mysteries of time, causality, and reality itself. And while the challenges of harnessing wormhole time dilation are immense, the possibilities are equally profound. This brings us to the next frontier, the role of wormholes in interstellar diplomacy. How might these cosmic shortcuts transform the way civilizations communicate, negotiate, and collaborate across the stars? The answer lies not just in the physics of wormholes, but in the potential for a new era of cosmic connection. What if the key to peace and collaboration across the stars lies hidden within the fabric of spacetime itself? Wormholes, those cosmic shortcuts through the universe, might not just revolutionize travel and trade, they could also transform the way civilizations communicate, negotiate, and work together. Imagine a future where diplomacy isn't limited by the vast distances of space, where alien cultures separated by light years can engage in real-time dialogue, sharing knowledge and forging alliances. This is the potential of wormholes as tools for interstellar diplomacy, a concept that could reshape how civilizations interact on a galactic scale. Picture this: two civilizations, one from a star system on the edge of the Milky Way and another from a distant galaxy, connected by a stable wormhole. Instead of waiting centuries for messages to travel between them, they can communicate instantly, exchanging ideas, resources, and even cultural artifacts. A diplomatic meeting that once would have taken generations to arrange could now happen in the blink of an eye. This kind of connection wouldn't just foster cooperation, it could lead to a new era of galactic unity, where civilizations work together to solve shared challenges like resource scarcity, cosmic threats, or technological stagnation. But interstellar diplomacy isn't without its challenges. For one, the sheer diversity of alien cultures could make communication and understanding difficult. How do you negotiate with a species that experiences time differently or has a completely alien concept of morality? And what happens if one civilization has a technological advantage over the other, creating a power imbalance in their relationship? These are the kinds of questions that would need to be addressed in a wormhole-enabled diplomatic network. Another hurdle is trust. Establishing a stable wormhole between two civilizations would require a level of cooperation and transparency that's unprecedented. After all, a wormhole isn't just a communication tool. It's a potential gateway for invasion or exploitation. To mitigate these risks, interstellar treaties and protocols would need to be established, ensuring that wormholes are used for peaceful purposes and that all parties feel secure. Despite these challenges, the potential benefits are immense. Wormholes could create a galaxy where civilizations are interconnected, sharing not just resources but also ideas, art, and philosophies. Imagine a galactic council where representatives from thousands of worlds come together to discuss the future of the cosmos, or a cultural exchange program that allows citizens from different star systems to experience each other's way of life. It's a vision of the universe as a thriving, interconnected community, where the barriers of distance and time no longer divide us. To bring this idea to life, let's consider a hypothetical scenario. Imagine a newly discovered civilization on a planet orbiting Proxima Centauri. Through a wormhole, humanity establishes contact and begins a dialogue. Over time, the two civilizations exchange not just technology and resources, but also stories, music, and traditions. This cultural exchange enriches both societies, sparking new ideas and innovations that neither could have achieved alone. The wormhole becomes more than just a tool, it's a bridge between worlds, fostering understanding and cooperation on a cosmic scale. As we explore these possibilities, it's worth reflecting on how much of the universe remains untapped. Wormholes, with their potential to connect civilizations, remind us that the cosmos is full of opportunities for collaboration and discovery. And while the challenges of interstellar diplomacy are immense, the rewards are equally profound. Now, as we turn our attention to the next frontier, let's dive into a mystery that has puzzled scientists for decades: the origin of cosmic rays. These high-energy particles, which bombard Earth from deep space, might hold clues about the nature of wormholes and the universe itself. So, let's explore how wormholes could help us solve the enigma of cosmic rays and uncover their cosmic origins. What if the high-energy particles constantly bombarding Earth from deep space cosmic rays hold a secret connection to wormholes? These mysterious particles, some of which carry energies millions of times greater than anything we can produce in particle accelerators, have puzzled scientists for over a century. Where do they come from, and what accelerates them to such incredible speeds? One intriguing possibility is that wormholes, those theoretical tunnels through spacetime, might play a role in their origin. Could these cosmic shortcuts be the unseen factories producing the universe's most energetic particles? To understand this idea, let's start with what we know about cosmic rays. First detected in the early 20th century, These particles, mostly protons and atomic nuclei, travel through space at nearly the speed of light. When they collide with Earth's atmosphere, they create showers of secondary particles, which scientists use to study their properties. While some cosmic rays originate from supernova or other violent astrophysical events, the most energetic ones remain a mystery. Their sources are often located far beyond our galaxy, and their extreme energies defy conventional explanations. This is where wormholes come in. Some theories suggest that the immense gravitational forces around wormholes could act as natural particle accelerators, boosting particles to the incredible speeds we observe in cosmic rays. As physicist Brian Cox explains, wormholes are like cosmic roller coasters, capable of accelerating particles to energies that rival the most powerful events in the universe. If a wormhole's intense gravity were to interact with nearby matter, it could fling particles outward with enough force to create the high-energy cosmic rays we detect on Earth. Another possibility is that wormholes themselves emit cosmic rays as a byproduct of their formation or collapse. Imagine a wormhole forming in a distant galaxy, its immense gravitational forces tearing apart nearby stars or gas clouds. The resulting energy release could produce a burst of high-energy particles, some of which might travel across the universe to reach us. It's like a cosmic fireworks display, with wormholes as the unseen spark. But how would we test this idea? One approach is to look for patterns in the arrival directions of cosmic rays. If wormholes are indeed sources, they might produce detectable signatures, such as clusters of cosmic rays coming from specific regions of the sky. Another strategy involves studying the energy distribution of cosmic rays. Wormholes, with their unique gravitational properties, could produce a distinct energy spectrum that sets them apart from other sources like supernova or black holes. The implications of this connection are profound. If wormholes are linked to cosmic rays, they could help us solve one of the biggest mysteries in astrophysics. They might also provide a new way to detect wormholes indirectly, offering clues about their locations and properties. As astrophysicist Priyamvada Natarajan notes, wormholes could be hiding in plain sight, their presence revealed by the cosmic rays they produce. It's a tantalizing possibility that could reshape our understanding of the universe. As we explore these ideas, it's worth reflecting on how much of the cosmos remains shrouded in mystery. Cosmic rays, wormholes, and the connections between them remind us that the universe is full of surprises, waiting to be uncovered. And while the journey to unlock these secrets is filled with challenges, the possibilities are as thrilling as they are profound. Now, as we turn our attention to the next frontier, let's delve into another fascinating phenomenon that might be linked to wormholes: gravity waves. These ripples in spacetime, first detected in 2015, could hold clues about the existence and behavior of wormholes. Could wormholes produce their own unique gravity wave signatures, offering a new way to detect these cosmic shortcuts? The answer might lie in the delicate dance of spacetime itself. What if the ripples in spacetime that we detect as gravity waves could reveal the presence of wormholes? It's a thrilling possibility that's capturing the attention of physicists and astronomers alike. Gravity waves, first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, are tiny distortions in the fabric of spacetime caused by massive cosmic events like black hole mergers or neutron-star collisions. These ripples carry information about the objects that created them, offering a new way to listen to the universe. But could wormholes, those theoretical tunnels through spacetime, also leave their mark in the form of gravity waves? the answer might lie in the unique way wormholes interact with spacetime itself. The idea stems from the way wormholes warp spacetime. Just as black holes and neutron stars create ripples when they merge or collide, a wormhole's immense gravitational forces could generate its own distinct gravity wave signature. Imagine a wormhole stretching or twisting spacetime as it forms, stabilizes, or collapses. These movements could send out ripples, much like a stone dropped into a pond, propagating across the universe and potentially reaching our detectors. The challenge, of course, is distinguishing these signals from the cacophony of other gravity wave sources. As physicist Kip Thorne explains, a wormhole's gravity waves would be subtle, like a whisper in a storm. But if we know what to listen for, we might just hear it. Recent advancements in gravitational wave astronomy are making this search more feasible. Instruments like LIGO and its European counterpart, Virgo, are becoming increasingly sensitive, capable of detecting even the faintest ripples in spacetime. In 2019, LIGO detected a mysterious event known as GW 1924-26, which some scientists speculated could have been caused by a wormhole. While the evidence was inconclusive, it sparked renewed interest in the possibility of wormhole-induced gravity waves. As astrophysicist Vicky Kalodra notes, every new detection pushes the boundaries of what we thought was possible. Wormholes might be the next frontier in gravitational wave astronomy. To better understand how wormholes could generate gravity waves, let's use an analogy. Picture two ends of a wormhole as the hands of a clock. If one hand moves, the other might respond, creating a synchronized motion. In the same way, if one end of a wormhole experiences a gravitational disturbance, say, from a nearby star or black hole, it could send ripples through the tunnel, producing gravity waves that we might detect. This interplay between wormholes and their surroundings could offer a unique fingerprint, helping us identify their presence even if they remain invisible to traditional telescopes. The implications of detecting wormhole-induced gravity waves are profound. It wouldn't just confirm the existence of these cosmic shortcuts, it could open up entirely new avenues for exploring the universe. Imagine mapping the locations of wormholes across the cosmos, using gravity waves as our guide. This could revolutionize our understanding of spacetime, revealing hidden connections between distant regions of the universe and even hinting at the existence of parallel universes. As we ponder these possibilities, it's worth reflecting on how far we've come in our ability to listen to the cosmos. From the first detection of gravity waves to the tantalizing hints of wormhole-induced ripples, each discovery brings us closer to unlocking the universe's deepest secrets. And while the journey is far from over, the progress we've made is a testament to the power of curiosity and innovation. Now, as we turn our attention to the next frontier, let's explore how wormholes might transform not just science, but the very way we experience the universe. Imagine a future where wormholes aren't just tools for exploration, they're gateways to interstellar tourism, offering ordinary people the chance to journey across the stars. What would that look like, and how might it change our relationship with the cosmos? Let's dive into the possibilities. What if the next great vacation destination wasn't a tropical island or a bustling city, but a distant star system light years away? This is the tantalizing promise of interstellar tourism made possible by wormholes, those cosmic shortcuts through spacetime. Imagine stepping through a portal and emerging in a world with twin suns, alien landscapes, and skies filled with stars you've never seen before. It's a vision that sounds like science fiction, but as we delve deeper into the science of wormholes, it's a future that might not be as far-fetched as it seems. The idea of interstellar tourism hinges on the ability to create stable, traversable wormholes that can safely transport humans across the cosmos. Picture a network of wormhole gateways, each one leading to a different star system or exotic location. A family could spend their summer exploring the vibrant jungles of an Earth-like exoplanet, while an adventurous traveler might book a trip to witness the breathtaking auroras of a planet orbiting a pulsar. The possibilities are as vast as the universe itself, offering experiences that would redefine what it means to travel. But let's not get ahead of ourselves. Interstellar tourism comes with its own set of challenges. For starters, stabilizing a wormhole large enough and safe enough for human travel would require technology that's far beyond our current capabilities. We'd need a way to generate and sustain exotic matter or negative energy, materials that defy our everyday understanding of physics. Even if we could create such a wormhole, there's the question of how to ensure its safety. Would radiation or gravitational forces inside the wormhole pose a threat to travelers? How would we guarantee that stepping through one end wouldn't deposit tourists into the heart of a collapsing star or the void of empty space? Then there's the logistics of interstellar tourism. How would we regulate travel between star systems? Would there be a cosmic customs office, checking passports and ensuring no one brings back alien microbes that could destabilize Earth's ecosystem? And who would own or operate these wormhole gateways? Would they be controlled by governments, corporations, or some kind of interstellar council? These are the kinds of questions that would need to be addressed before interstellar tourism could become a reality. Despite these hurdles, the idea of exploring distant worlds as casually as we visit different countries today is an inspiring one. It challenges us to think beyond the limits of our current technology and imagine a future where the stars are within reach. And while the journey to making this vision a reality is filled with obstacles, the progress we've made in understanding wormholes suggests that it's not entirely out of the question. As we ponder the potential of interstellar tourism, it's worth reflecting on how far we've come in our understanding of the universe. From the first telescopes that revealed the moons of Jupiter to the recent detection of gravity waves, each discovery brings us closer to unlocking the secrets of the cosmos. And just as wormholes could revolutionize travel, they might also hold the key to solving some of the universe's greatest mysteries. This brings us to the next frontier, the role of wormholes in unraveling the mystery of quasars. These incredibly bright objects, powered by supermassive black holes, have puzzled scientists for decades. Could wormholes be connected to their formation or behavior? The answer might lie in the strange and powerful forces at the heart of these cosmic beacons. Let's dive into this fascinating connection and explore how wormholes could shed light on one of the universe's most enigmatic phenomena. Quasars are some of the most dazzling and mysterious objects in the universe. These incredibly bright cosmic beacons, often found at the centers of distant galaxies, shine with the light of 1 trillion suns. For decades, scientists have puzzled over what could possibly power such immense energy output. The leading theory points to supermassive black holes, whose gravitational forces heat up surrounding gas and dust, creating the brilliant glow we observe. But what if there's more to the story? What if quasars aren't just powered by black holes? What if wormholes are playing a role too? The idea isn't as far-fetched as it might seem. Some researchers propose that wormholes could be intertwined with the mechanisms behind quasars, acting as conduits for energy or matter that fuels their incredible brightness. Imagine a wormhole funneling material from one part of the universe into the heart of a quasar, supercharging its energy output. As astrophysicist Priyamvada Natarajan explains, wormholes could be the hidden engines behind some of the universe's most energetic phenomena, including quasars. They might provide a way for matter and energy to flow in ways we're only beginning to understand. This theory hinges on the unique properties of wormholes and their ability to manipulate spacetime. If a wormhole were connected to a supermassive black hole at the center of a quasar, it could act like a cosmic siphon, drawing in matter and energy from distant regions and channeling it into the black hole's accretion disk. This influx of material would intensify the quasar's glow, potentially explaining why some quasars shine brighter than others. It's a bit like adding fuel to a fire. The more you pour in, the more it blazes. But how would we test this idea? One approach involves studying the light emitted by quasars. If wormholes are indeed involved, they might leave behind subtle signatures in the quasar's spectrum, tiny fluctuations or patterns that hint at their presence. Another strategy is to examine the motion of matter around quasars. If a wormhole is funneling material into the region, we might detect unusual flows or concentrations of gas and dust that defy conventional explanations. The implications of this connection are profound. If wormholes are linked to quasars, they could help us solve some of the biggest mysteries in astrophysics, from the origins of these luminous objects to the nature of the supermassive black holes that power them. It's a bold idea, one that challenges us to rethink what we know about the universe's most energetic phenomena. As physicist Brian Greene puts it, wormholes might not just be shortcuts through space, they could be the key to unlocking the secrets of quasars and the cosmic engines that drive them. As we explore these possibilities, it's worth reflecting on how much of the universe remains shrouded in mystery. Quasars, wormholes, and the connections between them remind us that the cosmos is full of surprises, waiting to be uncovered. And while the journey to unlock these secrets is filled with challenges, the progress we've made is a testament to the power of curiosity and innovation. Now, as we turn our attention to the next frontier, let's dive into another fascinating connection: the role of wormholes in generating dark energy. Could these cosmic shortcuts be the source of the mysterious force driving the universe's accelerating expansion? The answer might lie in the delicate interplay between wormholes, space-time, and the enigmatic energy that permeates the cosmos. What if the mysterious force driving the universe's accelerating expansion, dark energy, isn't just a property of space itself, but something generated by wormholes? It's a bold idea, but one that's gaining traction among physicists. Dark energy, which makes up about 68% of the universe, is the invisible force pushing galaxies apart faster and faster. Yet, despite its overwhelming presence, we still don't fully understand what it is or where it comes from. Could wormholes, those cosmic shortcuts through space-time, be the hidden source of this enigmatic energy? Let's dive into the science behind this intriguing possibility and explore what it could mean for our understanding of the cosmos. To understand how wormholes might generate dark energy, we need to revisit their unique properties. Wormholes are theorized to require exotic matter, a substance with negative energy density, to stay open. This exotic matter exerts a repulsive force, counteracting the immense gravitational pull that would otherwise collapse the wormhole. Now, imagine this repulsive force isn't confined to the wormhole itself. What if it spills out into the surrounding spacetime, creating a kind of pressure that pushes galaxies apart? This could explain the accelerated expansion we observe, with wormholes acting as cosmic fountains, spewing out dark energy into the universe. The scientific basis for this idea lies in the equations of general relativity, which allow for the possibility of negative energy influencing spacetime on large scales. If wormholes are scattered throughout the universe, perhaps as remnants of the Big Bang or as part of a cosmic network, their collective effect could mimic the behavior of dark energy. As physicist Lisa Randall explains, wormholes might not just be shortcuts through space, they could be the engines driving the universe's expansion, shaping the very fabric of reality. To make this concept more relatable, let's use a thought experiment. Picture the universe as a vast, inflating balloon. Each wormhole is like a tiny nozzle embedded in the balloon's surface, releasing bursts of air. These bursts create localized areas of expansion, but over time, their combined effect causes the entire balloon to inflate faster. In this analogy, the air represents dark energy, and the nozzles are wormholes, driving the universe's accelerated growth. The implications of this idea are profound. If wormholes are indeed generating dark energy, it could revolutionize our understanding of cosmology. We might need to rethink the origins of the universe, the nature of spacetime, and even the fate of the cosmos. For instance, if wormholes are the source of dark energy, their distribution and behavior could determine how fast the universe expands and whether it will eventually collapse or keep stretching forever. But the connection between wormholes and dark energy doesn't just reshape our understanding of the universe, it also opens up exciting possibilities for the future. If we could harness the energy generated by wormholes, it might provide a new way to power interstellar travel or even sustain life on a cosmic scale. And as we'll explore next, wormholes might not just be tools for exploration, they could also transform how we grow food and sustain civilizations across the stars. So, as we turn our attention to the next frontier, let's imagine a universe where wormholes aren't just gateways to distant worlds, but also the key to feeding humanity's interstellar colonies. How might wormholes revolutionize agriculture on a galactic scale? The answer lies in the strange and powerful connections between space-time, energy, and the future of food. Imagine a future where the bread on your table comes not from a local farm, but from a distant planet orbiting a star light years away. This is the tantalizing possibility of interstellar agriculture, made feasible by wormholes, those cosmic shortcuts through spacetime. In a universe where civilizations are spread across vast distances, ensuring food security becomes a monumental challenge. But what if wormholes could serve as the ultimate supply chain, enabling the exchange of agricultural resources between distant worlds? It's a vision that transforms the way we think about farming, sustainability, and the survival of interstellar civilizations. The concept of interstellar agriculture hinges on the ability to transport crops, seeds, and even livestock across the cosmos without the delays imposed by light years of distance. Wormholes, with their potential to connect distant points in spacetime, could make this a reality. Picture a colony on a barren exoplanet, struggling to grow food in harsh conditions. Through a wormhole, they could receive shipments of nutrient-rich soil, genetically engineered crops, or even livestock from an Earth-like world, ensuring their survival and prosperity. It's a bit like ordering groceries online, except the delivery truck is a cosmic portal that bridges the stars. But interstellar agriculture isn't just about survival, it's about diversity and innovation. Imagine a galaxy where civilizations share their unique crops and farming techniques, creating a vibrant exchange of agricultural knowledge. A world with a short growing season might import fast-growing crops from a planet with perpetual sunlight, while a colony with limited water resources could adopt drought-resistant plants developed on a desert world. This kind of collaboration could lead to breakthroughs in sustainable farming, benefiting all civilizations involved. Of course, the challenges are immense. Transporting agricultural resources through a wormhole would require precise control over the tunnel's stability and environment. Crops and livestock would need to survive the journey without being harmed by radiation, gravitational forces, or other cosmic hazards. There's also the question of logistics. How do you ensure that shipments arrive on time and in good condition? And what happens if a wormhole collapses mid-transport, leaving a colony without vital supplies? These are the kinds of hurdles that would need to be addressed before interstellar agriculture could become a reality. Despite these challenges, the potential benefits are too great to ignore. Wormholes could create a galaxy where no civilization goes hungry, where resources are shared equitably, and where the diversity of life flourishes across the stars. It's a vision of the universe as a thriving, interconnected community, where the challenges of distance and time are overcome through innovation and cooperation. As we explore the possibilities of interstellar agriculture, it's worth reflecting on how much of the universe remains untapped. Wormholes, with their potential to connect civilizations, remind us that the cosmos is full of opportunities for growth and discovery. And while the journey to unlocking these opportunities is filled with challenges, the progress we've made is a testament to the power of imagination and collaboration. Now, as we turn our attention to the next frontier, let's delve into another cosmic mystery that might be linked to wormholes: gamma-ray bursts. These incredibly energetic explosions, some of the most powerful events in the universe, have puzzled scientists for decades. Could wormholes be connected to their origins or behavior? The answer might lie in the strange and violent forces that shape the cosmos. Gamma-ray bursts are the universe's ultimate fireworks, short-lived, incredibly powerful explosions that release more energy in a few seconds than our sun will emit in its entire lifetime. These bursts, which can outshine entire galaxies, have puzzled scientists for decades. What cosmic events could possibly unleash such staggering amounts of energy? While most theories point to collapsing stars or merging neutron stars, there's another intriguing possibility. Could wormholes be involved? The idea that wormholes might be connected to gamma-ray bursts stems from their ability to manipulate spacetime on a massive scale. When a wormhole forms, stabilizes, or collapses, it generates immense gravitational forces and energy fluctuations. These events could, in theory, produce bursts of radiation so intense that they rival the most powerful explosions in the cosmos. As astrophysicist Neil Gehrels explains, wormholes are like cosmic pressure cookers. When they release their energy, the results could be catastrophic and spectacular. One scenario suggests that a collapsing wormhole could funnel matter and energy into a concentrated burst, creating a gamma-ray explosion visible across the universe. Another possibility is that wormholes act as natural particle accelerators, boosting particles to near light speeds and producing radiation as a byproduct. These ideas aren't just speculative, they're grounded in the mathematics of general relativity and quantum mechanics, which allow for such extreme energy releases. To better understand this connection, let's consider a thought experiment. Imagine a wormhole as a cosmic drain, pulling in matter and energy from its surroundings. If the wormhole collapses, that energy has to go somewhere, and one possibility is that it's expelled as a gamma-ray burst. It's like squeezing a balloon until it pops, releasing all the built-up pressure in an instant. This analogy, while simple, captures the essence of how wormholes might generate some of the universe's most energetic events. The implications of this idea are profound. If wormholes are indeed linked to gamma-ray bursts, it could revolutionize our understanding of these cosmic phenomena. Instead of viewing gamma-ray bursts as isolated events, we might see them as part of a larger cosmic network, with wormholes acting as the hidden engines behind their power. This could also open up new ways to detect wormholes indirectly by studying the unique signatures of gamma-ray bursts. As physicist Kip Thorne notes, gamma-ray bursts might be the universe's way of signaling the presence of wormholes, offering us a new window into the hidden structure of spacetime. As we explore this connection, it's worth reflecting on how much of the cosmos remains shrouded in mystery. Gamma-ray bursts, wormholes, and the forces that link them remind us that the universe is full of surprises, waiting to be uncovered. And while the journey to unlock these secrets is filled with challenges, the progress we've made is a testament to the power of curiosity and innovation. This brings us to the next frontier, the strange and mysterious world of wormhole-induced quantum fluctuations. What happens when the fabric of spacetime itself is stretched, twisted, or torn by these cosmic shortcuts? The answers might just take us to the very edge of what we thought was possible. What if the very fabric of reality is shaped by tiny, invisible ripples that wormholes could amplify or even control? This is the fascinating realm of wormhole-induced quantum fluctuations, where the strange behavior of particles at the smallest scales meets the cosmic power of spacetime tunnels. Quantum fluctuations are the heartbeat of the universe, the constant flicker of energy that exists even in the vacuum of space. They're the reason empty space isn't truly empty. It's a seething sea of particles popping in and out of existence. Now, imagine a wormhole threading through this quantum foam, its immense gravitational forces twisting and stretching spacetime. Could this cosmic shortcut influence those tiny fluctuations, creating ripples that echo across the universe? The scientific basis for this idea lies in the interplay between gravity and quantum mechanics. According to quantum theory, particles and energy are constantly fluctuating, even in a vacuum. These fluctuations are tiny, but they're everywhere, shaping the behavior of matter and energy on the smallest scales. Now, introduce a wormhole into the mix. Its gravitational field could act like a cosmic amplifier, magnifying these fluctuations and potentially creating observable effects. As physicist Leonard Susskind explains, wormholes don't just bend space, they can twist the quantum fabric of reality, creating patterns that might hold the key to some of the universe's deepest mysteries. One intriguing possibility is that wormholes could influence vacuum energy, the underlying energy of empty space that's thought to drive the universe's expansion. If a wormhole's gravitational forces interact with quantum fluctuations, they might create pockets of concentrated energy, potentially explaining phenomena like dark energy or even the early universe's rapid inflation. It's a bit like dropping a pebble into a calm pond. The ripples spread out, creating patterns that weren't there before. In this case, the pebble is a wormhole, and the pond is the quantum vacuum. To bring this idea to life, let's use a thought experiment. Imagine a spaceship hovering near a wormhole's event horizon. As quantum fluctuations ripple through the vacuum, the wormhole's gravity could distort these ripples, creating localized areas of higher or lower energy. These distortions might not just affect the spaceship, they could influence the behavior of nearby stars, galaxies, or even the fabric of spacetime itself. It's a concept that blurs the line between the microscopic and the cosmic, showing how wormholes could bridge the gap between quantum mechanics and general relativity. But what does this mean for our understanding of the universe? If wormholes can influence quantum fluctuations, they might hold the key to unifying these two great pillars of physics, quantum mechanics, and general relativity. This unification has been the holy grail of physics for decades, and wormholes could be the missing link. They could help us understand everything from the behavior of particles to the structure of spacetime, offering a new framework for exploring the cosmos. As we reflect on these possibilities, it's worth considering how much of the universe remains hidden from view. Wormhole-induced quantum fluctuations remind us that the cosmos is full of surprises waiting to be uncovered. And while the journey to unlock these secrets is filled with challenges, the progress we've made is a testament to the power of curiosity and imagination. This brings us to the next frontier, the role of wormholes in interstellar art and culture exchange. Imagine a future where wormholes aren't just tools for travel or science, they're gateways for sharing creativity, ideas, and cultural traditions across the stars. What might this look like, and how could it transform the way civilizations connect? Let's explore this fascinating intersection of art, culture, and cosmic exploration. Imagine a future where the vibrant art of one civilization inspires another on the opposite side of the galaxy, not through slow, centuries-long transmissions, but through the instant connection of a wormhole. This isn't just a dream, it's the potential of wormholes as conduits for interstellar art and culture exchange. In a universe where civilizations are separated by unimaginable distances, wormholes could bridge the gap, allowing ideas, creativity, and traditions to flow freely between worlds. Picture a painter on Earth collaborating in real time with a sculptor from a planet orbiting Proxima Centauri, or musicians from different star systems composing symphonies together. The possibilities are as limitless as the cosmos itself. The exchange of art and culture through wormholes wouldn't just enrich individual civilizations, it could transform the way we understand each other. Art has always been a universal language, transcending barriers of language, time, and distance. By sharing our stories, music, and visual creations, we could foster a deeper sense of connection and empathy across the stars. Imagine a gallery where works from 1,000 worlds are displayed, each piece offering a glimpse into the soul of its creator and the unique beauty of their home. As cultural anthropologist Dr. Elena Martinez notes, art is more than expression, it's a bridge between worlds. Wormholes could turn that bridge into a superhighway, connecting civilizations in ways we've never imagined. But interstellar art exchange isn't without its challenges. For one, the logistics of transporting art through a wormhole would require careful planning. How do you ensure that a delicate painting or sculpture survives the journey without being damaged by gravitational forces or radiation? And what happens if a wormhole collapses mid-transport, leaving priceless cultural artifacts lost in the void? These are the kinds of hurdles that would need to be addressed before art could flow freely across the stars. Then there's the question of interpretation. Art is deeply rooted in the culture that creates it, and what resonates with one civilization might be incomprehensible to another. Would aliens appreciate the emotional depth of a human symphony, or would they hear only noise? How do we ensure that the stories we share through art are understood and respected, rather than misinterpreted or lost in translation? These challenges highlight the need for cultural sensitivity and collaboration, as well as a willingness to learn from one another. Despite these hurdles, the potential benefits are immense. Wormholes could create a galaxy where creativity flourishes, where civilizations inspire and learn from one another, and where the boundaries of art are pushed to new heights. It's a vision of the universe as a thriving, interconnected community, where the exchange of ideas and culture enriches every corner of the cosmos. Now, as we turn our attention to the next frontier, let's delve into another cosmic mystery that might be linked to wormholes: the enigmatic nature of neutron stars. These incredibly dense objects, remnants of supernova explosions, have puzzled scientists for decades. Could wormholes play a role in their formation or behavior? The answer might lie in the strange and powerful forces that shape these cosmic giants. Neutron stars are among the most extreme objects in the universe, city-sized remnants of supernova explosions, packing the mass of a star into a sphere no wider than a small city. These cosmic powerhouses are so dense that a teaspoon of their material would weigh billions of tons on Earth. But what if these fascinating objects aren't just the end result of stellar explosions? What if they're also connected to wormholes, those theoretical tunnels through space-time? It's an idea that's sparking intense interest among astrophysicists, as it could reshape our understanding of both neutron stars and the cosmic shortcuts we call wormholes. The connection between neutron stars and wormholes stems from the immense gravitational forces at play. Neutron stars are born when massive stars collapse under their own gravity, leaving behind a core so dense that it warps spacetime in profound ways. This extreme curvature is eerily similar to the conditions required to create a wormhole. As physicist Kip Thorne explains, neutron stars are like cosmic laboratories for testing the limits of gravity. If wormholes exist, they might form in the extreme environments around these objects, hidden in plain sight. One intriguing possibility is that neutron stars could act as natural wormhole generators. As a neutron star spins, its intense magnetic fields and gravitational forces might create ripples in spacetime, forming microscopic wormholes. These wormholes could be fleeting, lasting only fractions of a second before collapsing, but their existence could have significant implications. For instance, they might explain some of the mysterious bursts of energy, like fast radio bursts that originate near neutron stars. As astrophysicist Priyamvada Natarajan notes, if neutron stars are producing wormholes, even briefly, they could be emitting signals that we're only just beginning to detect. But the relationship between neutron stars and wormholes doesn't stop there. Some theories suggest that wormholes could stabilize neutron stars, preventing them from collapsing further into black holes. Imagine a wormhole acting as a cosmic pressure valve, releasing excess energy and matter from the neutron star and keeping it in a delicate balance. This could explain why some neutron stars seem to defy the odds, surviving for billions of years without succumbing to the gravitational pull that should, in theory, crush them. To visualize this, think of a neutron star as a spinning top. As it spins, it wobbles slightly, creating ripples in spacetime. A wormhole could be like a tiny hole in the top, allowing energy to escape and keeping it from toppling over. While this analogy simplifies a complex idea, it captures the essence of how wormholes might interact with neutron stars, and how they could help us solve some of the most perplexing mysteries in astrophysics. The implications of this connection are profound. If neutron stars and wormholes are indeed linked, it could open up new ways to study both phenomena. By observing neutron stars, we might detect the subtle signatures of wormholes, offering clues about their formation and behavior. Conversely, studying wormholes could shed light on the inner workings of neutron stars, helping us understand their bizarre properties and the forces that shape them. As we explore these ideas, it's worth reflecting on how much of the universe remains hidden from view. Neutron stars and wormholes remind us that the cosmos is full of surprises, waiting to be uncovered. And while the journey to unlock these secrets is filled with challenges, the progress we've made is a testament to the power of curiosity and innovation. Now, as we turn our attention to the next frontier, let's delve into the fascinating concept of wormhole-induced spacetime curvature. What happens when a wormhole's immense gravitational forces twist and bend the fabric of the universe? The answer might just take us to the very edge of what we thought was possible. What if the very fabric of spacetime could be warped and twisted in ways we've only begun to imagine? Wormholes, those theoretical tunnels through the cosmos, might not just be shortcuts for travel. They could leave behind unique signatures in the curvature of spacetime itself. These signatures, if detected, could provide definitive proof of wormholes' existence and deepen our understanding of the universe's structure. But how exactly do wormholes bend spacetime, and what would it take to observe these distortions? The scientific basis for this idea lies in Einstein's theory of general relativity, which describes how massive objects warp spacetime. A wormhole, with its immense gravitational forces, would create a distinctive curvature, a kind of cosmic fingerprint that sets it apart from other objects like black holes or neutron stars. Unlike a black hole, which creates a one-way distortion, a wormhole's curvature would be more complex, with two ends connected by a tunnel that bridges distant regions of spacetime. As physicist Kip Thorne explains, wormholes don't just bend spacetime, they twist it into a shape that's unlike anything else in the universe. To visualize this, imagine pressing your finger into a soft piece of clay. The dent represents the curvature created by a massive object like a star or black hole. Now, imagine poking a second finger into the clay from the other side, connecting the two dents with a tunnel. This is the essence of a wormhole's spacetime curvature, a bridge between 2 points that distorts the surrounding fabric of reality. Detecting these distortions is no easy task, but recent advancements in gravitational wave astronomy are bringing us closer. Instruments like LIGO and Virgo, which detect ripples in spacetime caused by massive cosmic events, could potentially pick up the subtle signatures of wormhole-induced curvature. For example, if a wormhole were to form or collapse, it might produce gravitational waves with unique patterns, distinct from those created by black hole mergers or neutron star collisions. As astrophysicist Vicky Kalodra notes, the key lies in the subtle differences in the waveforms. If we can identify these patterns, we might finally detect a wormhole. The implications of such a discovery would be profound. It wouldn't just confirm the existence of wormholes, it could revolutionize our understanding of general relativity and the nature of spacetime itself. Wormholes might serve as natural laboratories for testing the limits of Einstein's theory, offering insights into phenomena like quantum gravity and the unification of physics. But the story doesn't end there. If wormholes can warp spacetime in detectable ways, they might also offer new opportunities for education and exploration. Imagine a future where students on Earth can study the curvature of spacetime firsthand, using wormholes as cosmic classrooms to learn about the universe's deepest mysteries. This brings us to the next frontier, the role of wormholes in interstellar education. How might these cosmic shortcuts transform the way we learn, teach, and share knowledge across the stars? The answer lies in the strange and powerful connections between spacetime, curiosity, and the human spirit. Let's explore this fascinating possibility next. Imagine a classroom where the teacher isn't just from another country, but from another star system entirely. This is the potential of wormholes as gateways for interstellar education, a future where the exchange of knowledge isn't limited by the vast distances of space. Wormholes, those cosmic shortcuts through spacetime, could revolutionize how civilizations share ideas, collaborate on research, and advance science and technology on a galactic scale. Picture a university where students from Earth attend lectures given by alien professors, or where groundbreaking discoveries made on a planet light years away are instantly accessible to scientists here. It's a vision that transforms the way we learn, teach, and grow as a species. The idea of interstellar education hinges on the ability to transmit information, not just data, but complex ideas, theories, and cultural knowledge across wormholes. Instead of waiting centuries for a message to reach its destination, civilizations could exchange knowledge in real time, creating a vibrant network of intellectual collaboration. For example, a breakthrough in quantum computing on a distant world could be shared instantly with researchers on Earth, accelerating technological progress exponentially. As astrophysicist Neil deGrasse Tyson puts it, wormholes could be the ultimate library cards, granting access to the collective knowledge of the cosmos. But interstellar education isn't just about sharing facts. It's about fostering understanding. Imagine a course on alien biology taught by a scientist from a water-covered exoplanet, or a workshop on interstellar diplomacy led by a scholar from a civilization that's been spacefaring for millennia. These exchanges wouldn't just enrich our knowledge, they'd broaden our perspectives, helping us see the universe through the eyes of others. As cultural anthropologist Dr. Elena Martinez explains, education is the key to empathy. By learning from other civilizations, we can build bridges of understanding that span the stars. Of course, the challenges are immense. Creating a stable wormhole capable of transmitting complex information would require technology far beyond our current capabilities. We'd need to ensure that data isn't distorted or lost during transit, and that the educational content is accessible to civilizations with vastly different languages, cultures, and ways of thinking. There's also the question of how to regulate interstellar education. Who decides what knowledge is shared, and how do we ensure that it's used ethically and responsibly? These are questions that would need to be addressed before interstellar education could become a reality. Despite these hurdles, the potential benefits are too great to ignore. Wormholes could create a galaxy where knowledge flows freely, where civilizations learn from one another, and where the boundaries of science and creativity are pushed to new heights. It's a vision of the universe as a thriving, interconnected community, united by a shared thirst for discovery. As we ponder the possibilities of interstellar education, it's worth reflecting on how much of the cosmos remains untapped. Wormholes, with their potential to connect civilizations, remind us that the universe is full of opportunities for growth and collaboration. And while the journey to unlocking these opportunities is filled with challenges, the progress we've made is a testament to the power of curiosity and imagination. Now, as we turn our attention to the next frontier, let's explore another cosmic mystery that might be linked to wormholes: the enigmatic nature of pulsars. These rapidly spinning neutron stars, often called the universe's lighthouses, have puzzled scientists for decades. Could wormholes play a role in their formation or behavior? The answer might lie in the strange and powerful forces that shape these cosmic beacons. Pulsars are the universe's cosmic lighthouses, rapidly spinning neutron stars that emit beams of radiation, sweeping across the cosmos like a celestial strobe light. These incredibly dense objects, remnants of supernova explosions, have fascinated scientists for decades. But what if there's more to pulsars than meets the eye? What if these spinning beacons are somehow connected to wormholes, those theoretical tunnels through spacetime? It's a bold idea, but one that's sparking intriguing discussions among astrophysicists. Could pulsars be more than just stellar remnants? Could they be gateways to understanding the hidden structure of the universe? The scientific basis for this connection lies in the extreme conditions surrounding pulsars. These objects are not only incredibly dense, but also rotate at mind-boggling speeds, some completing hundreds of revolutions per second. This rapid spin, combined with their intense magnetic fields, creates an environment where spacetime itself is stretched and twisted in profound ways. As physicist Kip Thorne explains, pulsars are like cosmic drills boring into the fabric of spacetime. If wormholes exist, they might form in the extreme distortions around these objects, hidden in the chaos of their rotation. One intriguing possibility is that pulsars could act as natural wormhole generators. As a pulsar spins, its immense gravitational forces might create ripples in spacetime, forming microscopic wormholes that flicker in and out of existence. These wormholes might be fleeting, lasting only fractions of a second before collapsing, but their presence could have significant implications. For instance, they might explain some of the mysterious bursts of energy, like fast radio bursts, that originate near pulsars. As astrophysicist Priyamvada Natarajan notes, if pulsars are producing wormholes, even briefly, they could be emitting signals that we're only just beginning to detect. But the relationship between pulsars and wormholes doesn't stop there. Some theories suggest that wormholes could influence the behavior of pulsars, acting as cosmic pressure valves that release excess energy and stabilize their rotation. Imagine a wormhole acting like a tiny escape hatch, allowing energy to flow out of the pulsar and preventing it from spinning out of control. This could explain why some pulsars seem to defy the odds, maintaining their rapid rotation for millions of years without slowing down. To visualize this, think of a pulsar as a spinning top. As it rotates, it wobbles slightly, creating ripples in spacetime. A wormhole could be like a tiny hole in the top, allowing energy to escape and keeping it from toppling over. While this analogy simplifies a complex idea, it captures the essence of how wormholes might interact with pulsars and how they could help us solve some of the most perplexing mysteries in astrophysics. The implications of this connection are profound. If pulsars and wormholes are indeed linked, it could open up new ways to study both phenomena. By observing pulsars, we might detect the subtle signatures of wormholes, offering clues about their formation and behavior. Conversely, studying wormholes could shed light on the inner workings of pulsars, helping us understand their bizarre properties and the forces that shape them. As we explore these ideas, it's worth reflecting on how much of the universe remains hidden from view. Pulsars and wormholes remind us that the cosmos is full of surprises, waiting to be uncovered. And while the journey to unlock these secrets is filled with challenges, the progress we've made is a testament to the power of curiosity and innovation. Now, as we turn our attention to the next frontier, let's delve into the fascinating concept of wormhole-induced cosmic inflation. What if these cosmic shortcuts played a role in the universe's rapid expansion after the Big Bang? Could wormholes be the hidden architects of the cosmos, shaping its structure on the grandest scales? The answers might just take us to the very edge of what we thought was possible. What if the universe's rapid expansion after the Big Bang wasn't just a random event, but something shaped by the hidden influence of wormholes? This is the intriguing possibility of wormhole-induced cosmic inflation, a theory that suggests these cosmic shortcuts might have played a pivotal role in the early universe's explosive growth. To understand this idea, let's rewind to the very beginning when the universe was just a fraction of a second old. At this point, spacetime wasn't the calm, orderly stage we know today. It was a seething, chaotic soup of energy and matter. In this primordial chaos, wormholes could have formed spontaneously, acting as cosmic catalysts for the rapid expansion that followed. The scientific basis for this idea lies in the interplay between wormholes and the inflatoned field, a mysterious form of energy thought to drive cosmic inflation. According to some theories, wormholes could have acted like pressure valves, releasing bursts of energy that fueled the universe's expansion. Imagine a pot of boiling water. If you suddenly remove the lid, steam rushes out, causing the water to bubble and churn. In the same way, wormholes might have allowed energy to flow out of the early universe, accelerating its growth and smoothing out its structure. As cosmologist Alan Guth, one of the pioneers of inflation theory, explains, wormholes could have been the hidden architects of the universe's expansion, shaping the cosmos in ways we're only beginning to understand. But how would this work in practice? One possibility is that wormholes created localized regions of spacetime with lower energy density, effectively creating pockets of negative pressure that pushed the universe apart. These regions would act like cosmic springs, driving the rapid expansion we observe in the cosmic microwave background, the faint afterglow of the Big Bang. It's a bit like inflating a balloon with tiny holes. The air escaping through the holes helps the balloon expand more quickly. In this analogy, the holes are wormholes, and the air is the energy driving cosmic inflation. The implications of this theory are profound. If wormholes played a role in cosmic inflation, it could reshape our understanding of the universe's origins and evolution. For instance, it might explain why the universe is so uniform on large scales, a mystery known as the horizon problem. Wormholes could have connected distant regions of the early universe, allowing them to reach a uniform temperature and density before they were pulled apart by expansion. As physicist Lisa Randall notes, wormholes might not just be cosmic shortcuts, they could be the key to understanding the universe's earliest moments and the forces that shaped it. This idea also raises fascinating questions about the nature of spacetime itself. If wormholes were present during cosmic inflation, could they still exist today, hidden in the fabric of reality? And if so, could they offer clues about the universe's ultimate fate? These are the kinds of questions that keep cosmologists up at night, pushing the boundaries of what we thought was possible. As we reflect on the role of wormholes in cosmic inflation, it's worth considering how this theory ties into the broader picture of interstellar travel. If wormholes shaped the universe's expansion, they might also hold the key to navigating its vast distances. The same forces that once accelerated the universe could one day help us traverse it, turning the cosmos from an insurmountable void into a navigable web of interconnected pathways. Now, as we near the conclusion of our journey, let's take a moment to tie together all the theories we've explored. From the early universe's rapid expansion to the potential for interstellar travel, wormholes have emerged as a unifying thread, connecting the deepest mysteries of the cosmos with humanity's boldest dreams. What began as a speculative idea has blossomed into a rich tapestry of scientific inquiry, offering glimpses into a future where the stars are within reach. And while the journey from theory to reality is still far from complete, the progress we've made is a testament to the power of curiosity, imagination, and the relentless pursuit of knowledge. So, as we prepare to wrap up this exploration, let's reflect on what we've learned and what it might mean for the future of humanity. The universe is full of surprises, and wormholes remind us that the greatest discoveries often begin with a spark of curiosity and a willingness to dream big. From the mind-bending Einstein-Rosen bridge to the tantalizing possibilities of traversable wormholes, we've journeyed through 45 groundbreaking theories that could forever change how we explore the cosmos. Each idea, from the exotic matter stabilizing wormholes to the holographic principles that might encode their secrets, offers a unique glimpse into the potential of these cosmic shortcuts. Whether they enable interstellar travel, connect parallel universes, or even serve as cosmic time machines, wormholes represent a frontier of science that challenges our understanding of space, time, and reality itself. But let's not forget the challenges. Stabilizing a wormhole, navigating its immense gravitational forces, and ensuring safe passage are hurdles that remain firmly in the realm of theory for now. The need for exotic matter, the complexities of quantum mechanics, and the ethical dilemmas of time travel remind us that the path to harnessing wormholes is as daunting as it is exciting. Yet, these challenges are also opportunities. They push us to innovate, to rethink the laws of physics, and to dream bigger than ever before. Imagine a future where wormholes are not just theoretical curiosities, but practical tools for humanity. A future where we travel to distant stars as easily as we cross continents, where civilizations separated by light years share knowledge in real time, and where the mysteries of the universe are unlocked one wormhole at a time. This isn't just science fiction. It's a vision grounded in the very real progress we've made in understanding these cosmic phenomena. As we stand on the brink of these possibilities, it's worth reflecting on what they mean for humanity. Wormholes remind us that the universe is vast, mysterious, and full of surprises. They challenge us to ask bold questions and seek answers that could reshape our place in the cosmos. In the words of Carl Sagan, somewhere, something incredible is waiting to be known. Wormholes might just be the key to unlocking that incredible something. So, what do you think? Could wormholes be the gateway to humanity's interstellar future? Or are they destined to remain a fascinating but unattainable dream? Share your thoughts in the comments below. We'd love to hear your perspective. And if you're as captivated by the mysteries of the universe as we are, don't forget to subscribe and join us for more deep dives into the wonders of space. The cosmos is full of secrets, and together we're just beginning to uncover them. Until next time, keep looking up, because the stars are closer than you think.